happier, closer to getting to the moon.
Good for NASA, good for America, good for all of us.
Robot drivers, start your robots!
Okay, so get that out.
We're replacing some of our rubber mounts.
Proceed hammer team, Edcuation and Lunabotics.
I think we did pretty good. We had a far break.
Future iterations of this competition.
By trade school, go tech school.
Just to really take massive volume of record.
Now, the exciting Caterpillar Autonomy Awards, and first place is Purdue University.
Top prize for Robotic Construction Award, first place, is awarded to the University of Illinois in Chicago.
I feel great. It's all the credit goes to the team. It's a total team effort that made this work.
The Artemis Award for the 2025 Lunabotics competition is awarded to the University of Utah.
But right now it's just surreal to think that we actually pulled it off.
Good morning and welcome to Day 3, the final day of NASA's Lunabotics 2026 event. We are broadcasting live from the amazing Center for Space Education facility here at NASA's Kennedy Space Center Visitor Complex here on Florida's East Coast. Speaking of Florida's East Coast, who saw that launch this morning? Yeah, you did. If you didn't, it woke you up for sure. My name is Kurt Lloyd. I'm a NASA software developer and robotics researcher, and I'm happy to be your MC, your narrator, and your color commentator. I want to give a big shout out to all the teams and staff and guests that are here in person at NASA. Let's hear you. Make some noise. All right. We're super excited for all of you who are watching this broadcast from all over the world. Whether you're watching live or whether you're watching this recording later, we want to thank you so much for your interest in NASA, for your interest in space exploration and lunar exploration, and for your interest in this event. Please don't be shy about sharing our Lunabotics website with everyone that you know. The link to NASA Lunabotics event website is go.nasa.gov/Lunabotics. That's go.nasa.gov/Lunabotics. And the links to all 3 of our daily live streams are right there at the top of the web page. We started on Tuesday, day 2 was Wednesday, and now day 3, Thursday. All 3 of those links are there. You can go watch the prior days, or now that you're here live, continue watching today live. We will start, that's no longer applicable. We have started our live stream every day, and this is our final day. Now, in case you're not familiar with NASA's lunar exploration plans, allow me to give you a quick high-level overview. A couple months ago, NASA's administrator, Jared Isaacman, publicly announced that NASA would switch to an accelerated and phased plan that will relatively quickly build a moon base on the lunar South Pole region. And the end goal of this new plan is to make a continuous and sustainable human presence that are living and working on the lunar surface. Now, some in the audience may be thinking, well, we did that back in the 70s, so why do it again? It is true that the accomplishments of the Apollo lunar program were quite amazing for that time. But that 70s technology could not sustain our astronauts living and working on the lunar surface for more than just a few days at a time. NASA's new lunar program, called Artemis, along with Administrator Isaacman's new accelerated and phased mission plan, gets us on a path toward an enduring human presence on the lunar surface. This new plan unlocks the scientific, the technological, and the economic benefits of lunar exploration. And so it provides a path and a plan to support long-term, even year-long human missions on the lunar surface, which is pretty exciting if you think about it. So where does this NASA Lunabotics competition fit into NASA's plans? I'm glad you asked. Lunabotics gives college and university student teams the task of designing and building working prototype lunar construction robots. During this competition, these student-designed and student-built robots will drive over complex and rugged moon-like terrain, and they will dig and transport fine particulate material or simulated moon dust from one location to another location in a timed event. We will measure the final volume of the pile of simulated moon dust that each robot creates during their timed event. And you probably guessed that a larger pile gives that team more points. There are a lot of other variables, though, to be aware of that complicate the scoring and add to the challenge for these student teams. But I'll go over some of those fine details as they come up during the timed competition events. I will be here the whole time to help explain what's going on. We had 47 teams compete last week in the Lunabotics qualifying event at the University of Central Florida in Orlando. And the top 10 teams from that event are right here, right now. These 10 teams, and you can see several of them behind me, are about to compete for the grand prize in NASA Lunabotics 2026 finals event. What we have on tap today is run 2, the final run for several teams. We are first going to see Michigan Tech take the robot through their second and final competition run. Then we will see New Mexico Institute of Technology. We will see University of Alabama, and then San Diego State University, Virginia Tech, and Iowa State. Those are the last 6 teams out of the 10 that are on deck to perform their second competition run. The 4 teams that I didn't mention out of the 10, they had their second run yesterday afternoon. So later, after this broadcast, feel free to go find the link for day 2 on our website, and you can watch those runs if you would like. All 3 days worth of live stream are going to be on YouTube and available to watch indefinitely after this competition is over. What I skipped over on the schedule just then was at 10 a.m. we are going to have a seminar. For those that are in the room, there's an important seminar at 10 a.m. It's Caterpillar's History with NASA, and that is going to be a really cool seminar. You don't want to miss that. We also will break for lunch somewhere in the noonish time frame. And it's not just a lunch break. Today's lunch break, we are also going to have a mini award ceremony. We're going to give out the Robot Innovation Award. So make sure you get some food from somewhere and then come back here because you don't want to miss the Robot Innovation Award. One other thing that is happening today is at 2:30 p.m., there's going to be a second seminar. This one is a student-led simulation capability seminar, and I believe Caterpillar is running that seminar as well. And then at the end of the day, probably at 4:30 p.m., although this entire schedule is subject to change, and we will make announcements if it does change, but probably at 4:30 p.m., we will be having the final award ceremony. Once I get the verification that that is the correct time, I will continually announce it throughout the day, especially if I just announced a wrong time. So that is what is on tap today. Don't forget to watch the prior recordings if you missed those, because there's some good stuff that you missed if you did miss those. And so as we look into our arena right now, we can see that the arena is still being prepared for our first run of the day, which is going to be Michigan Tech. So stay tuned, and we will entertain you with some random videos until the arena and Michigan Tech team are ready to go. So don't go anywhere, and thank you for watching NASA's 2026 Lunabotics Finals event. It's day 3, the final day of NASA's 2026 Lunabotics Finals competition. We're watching the Michigan Tech students in the mission control room of this competition, setting up their computers to talk to their robot, which we're seeing now, sitting powered on in our Lunabotics arena. The arena is set up with several feet depth of a crushed volcanic rock that simulates moon dirt to a high degree of accuracy. And these robots are charged with digging as much of this simulated moon dirt as they can in a 20-minute run, and to deposit as much of that simulated moon dirt as they are able into the scoring zone to be scanned by our 3D scanners to calculate how much volume of a hill they have made, or a berm. Moving dirt from one place to another on the moon has several uses in our future lunar mission plans. The scenario that we are kind of modeling this competition after, and their 20-minute run has started. And they're digging backwards. Things are happening fast here. This Michigan Tech robot lowers its scoop. You could kind of think of it as a front loader, but it is mounted backwards. So they lower that scoop and then they drive backwards in order to scoop up this granular material. And then, if I can get this camera figured out, they raise up that front scoop and dump it into their onboard hopper. Their onboard hopper is a conveyor belt, so it can move out of the way and make room for more material. This robot is digging. It's shifting slightly so that it doesn't dig in the same spot over and over. You could see the wheels shift right there. The wheels on this robot are unique. All of the wheels steer versus the wheels in your car where only the front wheels steer. This unique steering mechanism is used a lot in robotics. For example, our Mars rovers often have all of the wheels that are steerable, and that gives you a lot more options and a lot more agility to your robot. This robot can shift to the right or to the left by several inches or even several feet if it wanted to, without having to turn and then basically without having to do a 3-point turn. It basically instantly shifts very smoothly, and it doesn't waste any time. So this really increases this robot's productivity, and it also decreases the risk by not digging in the same spot over and over. Okay, it looks like they're heading towards the scoring zone. Very quickly heading towards the scoring zone. All right. This area between these 4 orange posts is the zone that we will be 3D scanning after the run to see how much material has been deposited by this robot. And there it goes. There's the first load. That's a lot. When you see a robot pause like that, oftentimes they're switching back and forth between manual mode and autonomous mode. So now I'm wondering if that was all done autonomously. If this team is that productive, what we just saw throughout this entire 20-minute run, and also has a certain level of autonomy happening throughout, they could really be a contender. This is exciting. Michigan Tech, their robot is doing really well just in the first 4 minutes. In this camera view in the upper right, you can see kind of a side view of the pile that they just deposited into the scoring zone. Okay, the robot has paused, and I see students typing in on the keyboard. Something may have happened with the robot. You'll notice these students in the control room have turned the monitors in front of them around. Those two monitors are NASA-supplied cameras, overhead cameras of the arena that the students are allowed to use during their run. There is a penalty associated with using those cameras, and so this particular team, Michigan Tech, has decided to not use our NASA-supplied cameras, which are simulating cameras on the lander, on the moon lander. They are only looking at cameras. This team is only looking at cameras that are on board their robot, which you can see on the screen right there. Okay, they're back in business. Whatever it was that happened just then, maybe some piece of software had stopped and they had to restart it. Maybe some computer on board the robot rebooted. There's a lot of situations that may have just happened to cause that. Still plenty of time, 14 and a half minutes. This robot's still being very productive. And it is scooching left and right and not digging in the exact same spot over and over and over. Hit a little resistance there. Okay, the students have, in the control room, have decided to take the hit and use the NASA-supplied overhead cameras. So that's going to affect their score, but they've made the decision that it's going to be necessary at this point. They're having some issues, and they didn't have enough visibility into what's happening. This is still a realistic mission scenario, though. The presumption is that this robot was dropped off on the moon by some sort of lander, and that that lander is, basically going to stick around and provide support to the robot that's performing this mission. That could be video support, could be power. This camera just showed us there's a little bit of a weird thing happening with their front digger. I hope that doesn't cause them any mechanical issues. Looks like it's still fine though. You can see from this close angle from this arena camera, which the students do not have access to this particular arena camera. They have access to a couple of our overhead cameras. You can see how full the hopper was on the robot just then. So this robot is weighed down very heavily right now based on how much material I see. This material is heavier than it looks. It is crushed volcanic rock, and it can get quite dense. It can and does get quite dense. So heavier than the same amount of beach sand, I would say, if that helps kind of get a feel for it. Not only is it heavier than the same amount of beach sand, it is really tough to dig into. It can compress and compact naturally, and it can feel almost as hard as concrete. So that's what these robots are having to deal with. The robot paused just then. I saw more typing on the keyboard. But the students appear to be understanding what's going on and able to react appropriately. This just goes to kind of show how realistic this lunar simulation is. You know, just like in a real life lunar mission, if something starts to go wrong with your robot that you're operating, you're going to be needing to look at the data and understand it and be able to react to it appropriately, not send any commands that might make things worse, and only you know, send commands that you think are appropriate and safe based on the situation. So not only have these students, all of these students from all of these teams, spent the entire academic school year designing and building and testing their robots at school, which is a really great experience. I mean, how many of us got to do that when we were in college? I'm quite jealous of what these students are experiencing all year long, being on these Lunabotics teams. If that's not amazing enough, these teams get to compete here at NASA, and you know, this real-time reaction as a robot driver for a robot that is, you know, in theory on the moon is really great experience, and these students are learning so much from this experience. I mean, you can't even quantify it. Just having this on the resume gives these students a real edge over new graduates that have not had this experience. Okay, we're doing a 3-point turn to get pointed in the right direction to deposit this material into the scoring zone. Just under 9 minutes remaining in Michigan Tech's second and final run. And this is a big load. They really pushed that one, and I imagine they're going to push the limits of this robot for the next 9 minutes, 8.5 minutes, because this is this is their last chance this year to make an impact and see if they can beat DuPage, honestly, in berm size, right? The robot seems to stop pulling roughly in the same spot each time. I think it's a little soft right there, right there. It goes downhill and it gets a little soft right there, I think. It's not a problem though. It's working for this team. I do worry that if it gets too soft there with a full load, I do worry about this robot in that area. Looks like they chose a slightly different angle now. 7 minutes remaining. In 7 minutes, do they have time to do this twice? Or is this their last cycle? Maybe they'll do 2 medium-sized loads instead of trying to go full. These are the decisions that the students are having to make real time. And it's not the entire team that's that's making these decisions, right? It's the 1, 2, 3, 4 students that are sitting in the mission control room are having to decide amongst themselves their plan and their reaction in real time. Of course, they have a plan going in, but things happen, and they have to adjust in real time. They're not phoning home. They're not allowed to. So there's a mix of, boy, that can be stressful, and boy, that is great experience for these students. I mean, real life engineering decision, real time decision making. It's a lot of material. I know these students have got to be happy with that. And they have 5 minutes left. So that only took a couple minutes. Okay, this time they're digging in this soft area. What I presume is a soft area. And that gives them a shorter distance to drive in order to deposit this material. And this robot's pretty fast, so, I mean, how long would you wait? What is the farthest you will go before you say, okay, it's time to drive? Is 30 seconds enough time? I'd probably give it 40, just to be a little conservative. That's just me guessing, though. These students have probably timed it and, you know, added a little bit of buffer and probably have a number that they're going for. When we hit this number, that's when we drive to the scoring zone. I believe there are 2 students, both operating joysticks, so one of them likely operating the digging and one of them likely operating the online conveyor belt, which you might notice the conveyor belt backs up now right here, and then they dump into it, and then when they're going back for more material, the conveyor belt will scooch forward toward the front of the robot, and it will pile up that material, and that allows them to build up the material on the conveyor belt into a smaller spot. The students had to jump back to the keyboard there for a second. That cost precious time with only 3 minutes remaining. That is a little frustrating, but the students were on it. They were fast. They were expecting it, whatever it was that failed there, and they reset or whatever needed to be done on the command line to get the robot back up. Under 3 minutes. They're probably going to keep digging up until they hit the magic number. Oh, they hit it, 3 minutes. Okay, I guess maybe they have time to do it one more time. So they chose to not overload their robot with one gigantic final dig. They decided to do multiple smaller loads. So still being a little conservative. What are they doing? Okay, I guess they're trying to make sure they get all of their material in the right spot. Got some in the front hopper that they're trying to deliver to. Alrighty, so they got 2 minutes left, just enough time to do one small load. Basically in that same spot they were just digging in. So really, I mean, how much time do they need to go back and dump? Is 20 seconds the right number? Or is that pushing it too much? Minute and a half. This is Michigan Tech's second and final run. And so this is, for all the marbles, whatever they can get here in the last couple minutes is going to be important for their final score in this competition. We are down to a minute. This will be a smaller load than the other ones, but you take what you can get. $50 seconds. $40 seconds. What's the magic number? That's it. 40 seconds. $20 seconds left. All right, they made it. They dumped their final material with 10 seconds to spare. Let's give Michigan Tech a big round of applause. That is a very good size, very respectable pile of material. We hope that gives them a good score. Coming up next is New Mexico Institute of Mining and Technology. It'll take our arena judges a few minutes to reset. They basically have to dig all of this material that Michigan Tech just deposited. They have to dig it all up and manually hand carry it over to the hole that Michigan Tech dug it out of and replace it and tamp it down and make it nice and compact. So that'll take a few minutes. But New Mexico Institute of Mining and Technology is queued up. They are ready to go into the bin as soon as our judges are ready. So don't go anywhere. New Mexico Institute of Mining and Technology coming up momentarily. You're looking at New Mexico Institute of Mining and Technology's lunar construction robot here, ready to compete, ready to run its second and final competition run here at NASA's 2026 Lunabotics event. We are broadcasting live from Kennedy Space Center's visitor complex, specifically a little building called the Center for Space Education, which is managed and run by the Astronauts Memorial Foundation. We couldn't do this project without help from all these amazing supporters and sponsors. Looks like this robot is ready to go. The students have left the arena. The judges are taking some data from the robot. Looks like the students in the mission control room have hands-on joysticks and are ready to control this robot either manually or autonomously. This robot is essentially a front-end loader. It has a wide bucket on the front, and it does not have an onboard hopper, so it will basically fill up its bucket and then drive that bucket full straight to the scoring zone. Between the digging zone and the scoring zone is an obstacle course that includes rocks and craters, and the entire arena is filled with several feet deep depth worth of crushed volcanic rock, which simulates to a high degree of detail what moon dirt feels like to a robot. And New Mexico has started their second and final run with 20 minutes on the clock. All right, they're digging in the same direction that they will be depositing the material for scoring. And they're probably going to go back and forth a few times in order to fill up their front end loader to the level that they are comfortable with or happy with. You'll notice this material that they're digging in isn't, I don't know what word, I want to say soft, like sand. It's not terribly easy to dig in. It resists your digging forces. This material, as I said, is crushed volcanic rock. And the moon dirt, it turns out, resists your digging forces in the same manner. So this is a pretty reasonable mechanical simulant of moon dirt, and NASA uses this simulant all the time to test our robots and equipment that need to interact with the lunar soil someday during their mission. Oh, they're getting a good bite that time. You can see how deep the rear wheels of this robot are digging in while they're pushing into this simulated moon dirt. This robot has really, really tall treads or grousers on its wheels, and that gives them the traction they need in order to really push their robot into this very tough material. The thing that a robot like this will have to be careful about is not sinking in too far, not spinning their wheels too much and sinking in too far. Because if you high center your robot in this material where the chassis is maybe being held up by the ground and the wheels are just kind of free spinning, that could be a bad situation for your robot. But if your robot has enough power, ooh, that's a good load right there. That one is full. If your robot has enough power and enough traction, there's a potential for that situation not to happen. That was a nice full bucket right there. New Mexico students have to be happy with that one. They appear to be stick driving this robot right now. It's unclear whether maybe during the start of their mission if they ran either a dig or a dump autonomously. Only the mission control judges know for sure if any part of this mission was performed autonomously. All right, let's get a nice big bite here. You can see if they, if their bucket is aimed at too sharp of an angle, they just hit hard material and don't make any progress. But if their bucket is too shallow, they just skim the surface and don't really pick up very much. So there's a fine line, there's a happy medium of bucket angle and how hard you press this thing into the dirt. But this team appears to fully understand the variables involved and know just the right amount of pressure to put on this bucket and the angle that is going to give them the biggest load. This team has purposely distributed most of the weight of the robot on the rear wheels so that it won't tip over when they have a full load in that front bucket. These are the sorts of things these students have to analyze and figure out before they ever build their robot. Oh, look how deep those rear wheels are. Luckily, it's not getting stuck. This robot digs itself in very deep when it's pushing, which worries me a little bit, but it looks like those really, really tall treads or grousers on those wheels are enough to allow this robot to dig itself out of any hole it may dig itself into. All right, making very good progress here. Only 6 minutes in, and this robot is a little workhorse. It's powerful. It's dependable. That's a big scoop right there. That's a lot of material. I mean, it's overflowing. New Mexico appears to be having a great run in their second and final competition run here. Just working hard, making little or no mistakes. Appears to be stick driven by the students, at least right now. "12 minutes left, plenty of time to just continue building that berm." It's a little soft right there where the robot is making essentially a 90-degree turn. But this robot doesn't seem to be bothered by that soft material. So the simulated moon dirt can be hard, but it can also be soft. It just depends on whether it's kind of been sitting there a while and been compacted over eons, or whether it's been fluffed up by a recent robot's wheels, for example, which is what we see a lot in this competition. Our judges tamp down and compact the material in order to make it the same between event to event. And then sometimes robots will inadvertently fluff up the material and then kind of have trouble with that material that's been fluffed up. But this New Mexico robot does not appear to have any trouble driving in material that's been fluffed up. The robot just stopped. I see hands on keyboard. Look how deep that spot is right there. They've been digging in that same spot for a while, and they've made quite a hill. This is a very heavy load for this robot, especially if it's driving downhill. That kind of takes their center of gravity over the front wheels, their center of mass over the front wheels, and made them tip forward a little bit. So they lost a little material to that tipping motion a little bit ago, but still ended up with a very, very full bucket that just went into the scoring zone. 9.5 minutes remain. So we're just over half done with this second and final run for New Mexico Institute of Mining and Technology. And they have a very respectable pile of simulated lunar soil in the scoring zone. All right, their digging was a little bit unbalanced just then. It was just on one corner of their bucket, so they're going to need to try a different spot. They're getting good bucketfuls in that spot, but here's the problem: they're making quite a hill. They're making quite a crater. they're making a hole right there. Okay, let's just call it a hole, which means if the back of the robot is on the uphill side, it makes the front of the robot tip over. Will the team continue in the same spot for the next 8.5 minutes? Or will they say, you know what, this is getting a little dangerous. I mean, these students might be saying, I'm not afraid of this hole. Let's keep going. And I respect that. Yeah, it's real soft right there where they're digging. They're going to look how much is in their bucket. Wow, that is a lot of material. So much that the robot cannot pick up their bucket right now without tipping over. Could be just because the back end of the robot was higher. Once they get on level ground, they may be good. Yep, looks like they're good now that they're on level ground. Wow, they're getting a little more aggressive in the second half of, wow, I don't think that bucket could hold much more than that. So we'll likely see that same aggressiveness for over the next 7 minutes. This is a great camera angle to watch this this digging. Yeah, they're just making this hole deeper and deeper. Which is fine. It seems like the robot can handle it and is not scared of a little hole. Because that is what's maximizing the amount of material in their bucket. 6.5 minutes remain. That is a nice big berm right there. From this side angle, you can see how deep that robot is. It's almost invisible. It's almost below grade. Oh my goodness. That is another big bucket full. Look how deep that robot is. Our arena judges are gonna have fun filling in this hole after this event is over. Wow, that's like 2 feet deep. This robot is strong enough to climb up out of that hole even when filled. Very impressive. A lot of robots would have trouble climbing out of that hole, even empty, let alone with a full load. Same exact spot. It's working for him. Why change now? Oh my goodness, that is a lot of material. Oh man. Okay, get out of that hole. There you go. Center of mass has flipped so that it's between the front axle and the rear axle, but now they're on level ground. Are they going to tip again? Nope, they're good. They didn't lose. They didn't spill very much at all. That is a really, really big, full, overflowing scoop right there. 4 minutes remain for New Mexico. These students have to be so excited with this run. Smiles all around in the mission control room. We have what looks like one student controlling this robot with a joystick and 3 students encouraging him. Oh, that is a deep hole. Look at camera 3 again real quick. That robot is almost disappearing beneath the surface. That's crazy. Well, alrighty, get yourself up out of that hole now. Nicely done. I think it gets a little harder each time to get up out of that hole, but there's only 3 minutes left, so I'm not suggesting they change anything at this point. It is definitely working for them. Oh, typing on the keyboard. Something happened. Back on the joystick. 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 There we go. These students, obviously, all the students that are competing this week, obviously have a lot of stick time with their robots, a lot of experience running them in various situations. They're going for more. They're going for more. We got a full bucket, but we're going to go for more. That is a lot. Man, just turning in that hole is not easy, let alone driving up out of it. They're getting a little out of it and then turning, which falls back in a little bit. Ugh. They lost some material there, but not a ton. Not a ton. They still have a very, very full, technically still overflowing bucket after that little spill. A minute and a half. I'm going to say this out loud. Some of that material is outside the scoring zone. Sadly, that's hard to see. That's hard to watch, but some of that material is falling outside of the zone that our 3D scanner is considered scoring material. And I've said this before, we, watching this broadcast, have access to a lot more cameras and better camera views than the students. So it's sad, but not surprising that the students don't realize that some of that material is being deposited outside of the scoring zone. Okay, we're under 30 seconds. What can they get in 30 seconds? Are they done? Or are they going back for more? 20 seconds. Go, 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 go. What can they do? 15 seconds. 10. Okay, they're done. They're done. They're just celebrating. Let's give New Mexico Institute of Mining and Technology a big round of applause. What an amazing run. They've got to be super happy with that pile. If we look at this view, you can kind of get a sense for how big that pile is. If we look at the Arena 1 camera, we get a little bit lower perspective. Okay, so the pile is up in the upper right. Oh, it's a little bit covered up by the label. I apologize. Hopefully in the next few minutes we will be able to show you the live scan, or the scan from our 3D scanner, and we'll get a sense for how big their pile is. We're not going to give you a number, but the judges obviously are getting that number. Whew, man, okay, good job, New Mexico. If you were thinking about leaving this broadcast, now is not the time. Up next is University of Alabama. This team is looking to do an amazing second run, and they're looking to, like all teams, they're hoping to win this competition. So don't go anywhere, because you don't want to miss University of Alabama coming up next, live on NASA's 2025 Lunabotics competition. Oh, here's the scan of New Mexico's run. Enjoy this visual of New Mexico's scored material while we reset the field and prepare for University of Alabama coming up next.
This competition for NASA is part of their Centennial Challenge program. What we're going to see this week is 2 teams who have made it to the final step be able to actually print a 1/3 scale habitat that may ultimately be used on the surface of Mars.
The kind of materials they have selected to build these habitats are materials that will represent what could be found on the surface of the moon or on the surface of Mars, perhaps.
It's really a form of incentivized R&D where NASA provides prize money to pursue innovation that meets, again, NASA's mission objectives of space exploration, but also can provide real value for here terrestrially. A great example is the work we did with NASA at Johnson Space Center, where we worked on remote control and creating an operator center so he can drive a machine, could be many miles away. And that operator center actually moved forward, and you can see it today in Caterpillar's command for dozing product, for example. And so certainly this technology that we're looking at this week has that opportunity of being a very disruptive, transformational technology for even the construction industry here on Earth.
NASA was interested in working with Caterpillar because they have experience, of course, in construction. And if we want to build habitats, we go to the experts, right? So we are reaching out to the people that have done this for years and years to help us make sure that what we're doing makes sense.
I think this competition, is a public example of what we do here at Caterpillar every day. There may be a public image of Caterpillar and we certainly are a manufacturer of heavy equipment, but really we are a technology company, and we provide that technology through large equipment like you see behind me here. We provide that technology through large equipment and services that we provide. I believe that's who Caterpillar really is.
You are watching live from NASA's Kennedy Space Center. The University of Alabama team robot is in our Lunabotics arena, and it is getting ready to perform. It's getting ready to compete in its second competition run of 2. So this is the chance for this Alabama team to show what the robot can do. And you know Alabama wants to win this event. So the more automation this team can do and the larger the berm they can make is what it's going to take for Alabama to walk away with the big major trophy. It is the combination, here we can see the judges turning away those screens. The Alabama team is declining those camera views in order to maximize their points. The Alabama team has all the data and video feeds that they need from their robot. There's a lot of autonomy in this robot, a lot of sensors, and you will probably see, as the timer is about to start, you'll probably see a lot of autonomous operations here in this Alabama. Oh, that was the end of the setup time. So there's going to be it's going to take a couple minutes to put the final touches and make sure everything is ready to go, and then our judges will start a 20-minute timer for this Alabama robot. All teams in this competition are strongly encouraged to do autonomy, and there's several ways that we encourage teams to design and build and create autonomy into their robotic systems. We give them bonuses for each leg of their mission that they perform autonomously. For example, digging is one leg that they can choose to do autonomously. Transporting from the digging area over across the obstacle zone into the construction zone is a second option. And the 20-minute timer is about to start. And autonomous delivery or autonomous dumping is another option. Those are kind of like 3 a la carte areas that teams may or may not choose to perform autonomously. But there's one more autonomous mode. The students are hands off, so this robot is spinning around autonomously in order to, I presume, make a map of the arena, a 3D map, very likely. The grandfather of autonomy in this event, okay, the digger has spun up. The grandfather of autonomy in this competition is what we call, quote unquote, full autonomy. And that would mean that the students were completely hands off for the entire competition run without touching a single joystick or a single keyboard. That gives, if that happened in this competition, that would basically win this competition by a landslide, assuming that material was deposited. But essentially, full autonomy is awarded so many points. It's really hard to beat with practically any amount of manual operations. At least that's what I've heard. I haven't actually sat down and done the math and tried all kinds of different permutations, but you know these students have, and that's what I have heard the students say many times. 18 minutes, so 2 minutes. In the first 2 minutes, this robot has apparently mapped the arena, and has performed an autonomous, I presume, digging operation. It's doing some more digging, and the students appear to be hands-off in mission control. Ooh, it's trying to turn, but I think the students are going to need to step in right here because robot is trying to turn, but it still has its digger pretty much buried in the ground. And if the students don't step in, this robot is going to get pretty deep with those wheels just kind of spinning and working against nothing. All right, so the students are raising up the digging implement, clearing it, and I don't think this robot is buried or high-centered. It should be able to drive out of this hole. Question is, are the students going to activate autonomous transport? I believe that's what they did because I see hands off in the control room. Now turning in place can be quite a feat in this simulated moon dirt. This robot is doing it. It's not easy, but this robot from University of Alabama is turning in place in this moon dirt. You see the robot has a certain amount of traction on its wheels. It also has basically a lot of hollow areas in its wheels that don't push sideways against this material. That was possibly a mapping motion. The first mapping motion may have been to find an appropriate digging spot. This mapping motion that we presumably just saw may have been to find a safe path over to the construction area, which is in the upper right of the screen, which is where this robot needs to deposit the material that it just dug. The robot is in motion. It appears to be autonomous because I see no hands on keyboards, no hands on joysticks. I'm not even sure this Alabama team uses joysticks, to be honest. Okay, it might be pausing to do some more mapping. I mean, I've done some autonomous software and used various autonomy sensors. For example, the can-shaped sensor centered on the top of the robot with the white lid is a laser scanner. Probably a laser scanner that can see all the way around the robot, 360 degrees. So the robot decided not to go straight, but to turn a little bit. And so presumably now it's going to turn before it hits this wall. It probably saw some rocks when it did its mapping scan earlier. When a robot just spins in place like this, it's probably scanning, 3D scanning the area. The good news is once the robot has fully scanned the arena, it doesn't have to ever do it again. It'll just drive and drive and drive and drive. What the robot wants to do is probably avoid those rocks on the left and obviously not run into that column on its right. This is taking a bit of precious time, and so this is a decision that each team has to decide for themselves. autonomy in general, not always, but a lot of times is slower than just manually stick driving a robot. You know, drive it like you stole it style. And so each team, knowing that, gets to decide whether the autonomy points are worth it. So this robot is perfectly driving between the column and the rocks. And so now there's a couple more rocks that I'm not sure the robot knows about yet. And the column. Alrighty, it knows about them because it's driving forward. And so as soon as the robot crosses the orange line there on the ground, it is technically in the construction zone. And so if autonomy happens in the construction zone from here to the deposition of the material, that's another autonomous mode that a lot of teams will choose to try out. They've made it still presumably automated this entire time. There is a rock there. If you try and turn right, that rock's going to be against your wheel, which I presume that's what the robot wants to do. It wants to dump in a location that is farther to the left, because it's been programmed to do so. Here it goes. Very likely autonomous. Just by looking at the students in the mission control room, and the body language, and the fact that their hands are in their laps and they don't appear to be touching any controls, I believe everything we've seen since the start of this run has been autonomous. Ten and a half minutes remain, so we are close to the halfway point. Yeah, the robot did kind of sort of brush against that rock, but it did not appear to be a big enough problem for the students to step in and cancel their autonomy. So it looks like we're still running autonomous. As slow as this appears, you know the students could drive this robot faster than it's running right now in autonomous mode, but that's one of the trade-offs that the students have thought about and made the decision to keep the autonomy even though it's slower, because the points that are awarded for autonomy make it really worth doing and continuing if it's still making progress and being productive. 9 minutes left. So it took nearly 10 minutes to perform that first dig, transport, dump cycle. But as I said earlier, all the remaining cycles do not have to map the entire arena. So in theory, they should go faster. Ooh, there's a rock right there. Not sure this robot is designed to ingest a rock like that, of that size. It's a good thing that rock did not jam up the works. All right, so in the time remaining, you can see the wheels moving very slowly, so it's made it to the depth, the digging depth it wanted, and it is driving forward Okay, the digger's being lifted and going back down. I think that action where it lifts and then goes back down for another bite, I think that might be related to trying to pack in the material on board the robot in order to maximize the onboard capacity. 7 minutes. I suspect this robot can make 2 trips in its, last 10 minutes of its run here. You can see how big that hole is that this robot has dug into. This is a strong, powerful robot to be able to dig that deep. Because this material, even though it kind of looks like light and fluffy, it is very compact. It is quite hard, just a few inches under the surface. And that is a deep hole. So this robot, oh yeah, you can see now from this angle, it's kind of pushing. It's on board. Okay, now I think they're all the way up. I think they're going to drive. Here we go. All right, if this goes as quickly, I know it's a little slow. I think the timing is such that they'll be able to do this, deliver this load, and then do one more. Assuming the robot doesn't run into that post in the middle of our arena. Nope. Looks like the right wheels are slipping more than the left ones. The upper wheels on this view appear to be slipping more than the lower wheels, which is making the robot not drive perfectly straight. But it was going uphill, and it does make a lot of sense that, one area, one spot might have been looser than another spot. Welcome to real life. That happens a lot in the real world. Based on that overhead view we were just looking at, I think this robot has a lot of material on board. I think this second pile is going to be bigger than the first pile we saw. And I think everything we've seen has been autonomous, which is really, really good scoring-wise for this Alabama team. All right, we're under 5 minutes left. So assuming this robot dumps relatively quickly, they will have time to do one more very, very, very full trip. Four minutes and 20 seconds remaining. So here's a big decision for the students. Knowing how long it takes, or how long it took to do that last trip, honestly, those piles look about the same size to me. Now the students are doing calculations, right? Knowing how long it took to do that last trip, is it going to work out? Is this, if they allow the autonomy to continue, they will get bonus autonomy points. But what if it does not make it back in time, this autonomy software, in order to deliver before the timer runs out in 3 minutes and 40 seconds? Would it be better to leave autonomy running and end up with only those 2 piles, those 2 delivery piles? Or would it be better to take over manual control, drive it like you stole it in the last 3 minutes, and add to the official scored material? Ooh, it's hitting some hard stuff right there. That may be hitting rocky material. There are rocks embedded in this lunar simulant. There are some gravel-sized rocks, but some of them are bigger. Two and a half minutes. I'm starting to fear that this robot being left in autonomous mode is going to be left with the timer running out and not delivering this last load. But the students they may be okay with that, since they're going to get the autonomy points. Okay. I don't know if the students stepped in. This load is not as big as the other one. I don't know if the students stepped in and said, okay, cancel the autonomous digging and jump right into autonomous delivery. I suspect, since the robot didn't dig nearly as much as it did earlier, that that's what happened just then. So they may have given up a little bit. They may have given up on one autonomous leg in order to at least deliver this material in the last minute of their run. The speed of this robot implies to me that it is autonomous. So it's quite possible that this Alabama team will not get, I'm assuming this Alabama team is not going to get full autonomy, quote unquote full autonomy, but they're going to get very many repeated partial autonomy points. Basically, lots of digging autonomy, lots of delivery autonomy, and lots of transportation autonomy. Yeah, there wasn't a whole lot on board that time, but I do understand that the students decided to go ahead and deliver it. So there's two large piles and one small pile, a smile pile, that was delivered. Let's give University of Alabama a big round of applause. There was so much autonomy that happened just then. It's going to be interesting to see what that gets them as far as standing for the overall prize. Great job, University of Alabama. You should be very proud of your robot, proud of your students for creating such a highly autonomous robot that delivered two really big full loads during that 20-minute run. Now, coming up next, we should have enough time to do one before lunch, right? Coming up next is going to be Virginia Tech. If that's surprising to you and you were expecting me to say San Diego State, Virginia Tech and San Diego State have agreed to swap order. There's been some cooperation happening, and San Diego State and Virginia Tech have agreed to swap. So Virginia Tech is going to run next, and then I don't know if we'll have time to do another one before lunch, but after Virginia Tech is going to be San Diego State, and then after San Diego State is going to be Iowa State. So don't go anywhere. You don't want to miss these last three robots that are competing in NASA's 2026 Lunabotics Finals event. And don't forget, when we do break for lunch, we will also have another mini award ceremony. We will be having the Robot Innovation Award. You do not want to miss that. So whenever lunch happens, don't disappear. You might miss the Robot Innovation Award. You are watching NASA's 2026 Lunabotics Collegiate Competition live streaming today, our final day of competition, live streaming from NASA's Kennedy Space Center Visitor Complex. In our simulated lunar soil arena is the Virginia Tech robot. This is the second run, the second competition run, and final competition run for Virginia Tech and all of our other teams that we're going to see run today. Students have placed their robot in the starting position, while other students are have set up their command and control and monitoring system in our Mission Control Center, which is on the opposite side of the building, which means the students who are controlling this robot, and we've started, the students who are controlling this robot are only able to see data from their robot and video feeds from their robot. These students have chosen one video feed from NASA to monitor and to take a little bit of a penalty in order to have access to that video feed. This robot from Virginia Tech has a front-loading digger bucket and an onboard hopper, so they can take many, many bites with the front bucket and store all those bites of material on board, and then take less trips over to the scoring area to deposit the material. Lunabotics simulates a mission on the moon that is intended to build a berm, B-E-R-M, and it's basically a hill, a pile of material that can be used for many things. It could be used to protect sensitive equipment from high velocity particles that will ultimately be flying around on the moon during various landings of various equipment. It can also be used, the moon dirt on the moon can also be used to just pile directly on top of sensitive equipment in order to create, whoa, what are they doing? They're, I'm sorry, this camera's a little hard to control. They went straight over those rocks that are between the starting area and the scoring area. I don't know, we'll have to find out later if that was an autonomous move for this robot or if the team just decided to try it. The team is clapping. The robot has made it over that rock. I did not think that was going to succeed. Okay, that was kind of crazy. That was a very risky move. I suspect the judges will tell you that it's technically allowed. I'm sure the judges put those rocks there in order to discourage teams from doing that, but I suspect that the rules allow it. Only the judges know for sure, though. 16.5 minutes remaining. They may have found a shortcut that other teams have not tried. Other teams who maybe didn't want to take the risk. So, let's see, with 16.5 minutes remaining, math is hard. In the first 3.5 minutes, this Virginia Tech team has dug and deposited their first load, essentially finding a shortcut over some pretty sizable rocks that were placed by our judging staff between the starting zone and the scoring zone. Is this Virginia Tech team going to do that this entire run, or did they decide, boy, that was scary. Let's not do that again. Oh, their rear door looked like it was open just then, and it closed a little bit. This team, if they were running manually, here they go again. If they were running manually, which is quite possible, they may have forgotten to close their door. Here they go, backing full speed over those two rocks with their tracks and not having much issue. It looks like they might be partially stuck, maybe. If they get high centered on one of those rocks and their tracks are no longer giving them traction, that is disastrous for this robot. Okay. Oh, they're changing the center of mass by lifting their load and getting it more towards the back of the robot. That appears to have possibly worked by moving their center of mass towards the back of the robot. They have gotten over that rock. That is crazy. So they appear to have now put 2 full loads from the robot into the scoring zone using a possible shortcut that no other team has tried. Not because the other teams didn't think about it. I'm sure many teams wondered, boy, can we just take that shortcut right there? But until now, no team took that risk and decided it's worth the risk. And you saw a little bit of that risk when that robot got high-centered for just a moment, and it looked a little scary there, but the robot got out of it. All right, this time they're going for a lot, trying to maximize their onboard load, getting just a little bite each time. 12.5 minutes remain. They lifted up their onboard hopper just then, probably to push all the material towards the back, allowing more room for more to be deposited. This robot can fit a lot on board. Okay, are they going to take the long route this time? Looks like it. They were on that side of the arena anyway. This is a really big load right here. Virginia Tech Okay, this was autonomous. I saw hands go up in the control room. They're not touching their computers or their joysticks. And it looks like all of that material has slid out. Got to be happy with that. So they got some autonomy points just then, presumably. And they're going for the shortcut, which, I mean, if that rock has moved, it may not really be scary for them anymore. I think they've spread out those rocks that were sort of almost creating a barricade earlier. And back to digging. I suspect that this is manual digging, but I don't know for sure. So I just don't have that visibility. That was a good scoop. That was a lot. Go. Focus on that area right there. You can see how the front of the robot lifts up. Its wheels lift up off the surface when it's pushing that front bucket in. They're using all the power that this robot has to push their bucket. Into the simulated lunar soil. All right, looks like they're going for the shortcut again. With 8 minutes remaining for Virginia Tech. Oh, ugh. Well, this is going to be a great view of their door opening and the material that comes out. And if they drive with that door open, it helps shake the material out even more. Back to digging with 7.5 minutes remaining. Plenty of time. Plenty of time to build on that berm that they have started, make it bigger. If we look at the students in mission control, we can see one student has a baby joystick. They showed me that earlier. It's a toy. It's their good luck charm. He's not actually controlling the robot with that. But it's hard for me to tell whether that other student with his back to the camera is joysticking this robot. I suspect that that is the case, although only the mission control judge knows for sure how much of this That's a full load. How much of this run is manual and how much is autonomous? Taking the shortcut again. Basically one wheel on the dirt and one wheel on a rock. I mean track. This is a rubber tracked robot. Even though it's taking a shortcut, when it did take the long way around, it didn't seem to have any trouble with mobility. You can see how this stuff needs a little bit of help to make it flow. This material is sticky, is a word that we sometimes use. It's not wet. It's not sticking because it's wet. It's sticking because the particles are very fine and also jagged in shape. And that combination makes these particles kind of lock together like little puzzle pieces that can make them stick to your hopper and not want to flow nicely. It can also make them very compact when you're trying to dig them. And you can see how many of these robots really, power through, really push hard in order to dig in this stuff. And that's partially because of the particle size and the particle shape and how sticky they become. They're basically compacting together very naturally into a hard surface. The hard surface can feel a little bit like concrete until you kind of break through. Ooh, there's something weird happened there, but it looks like it's okay. Down to 3.5 minutes for Virginia Tech. This is their second and final run. They want to maximize their autonomy if they want to go for the grand prize, and they want to maximize the amount of material that they deposit if they want to go for a secondary prize, which is we call the robotic construction prize. Virginia Tech has to be pleased with this second run with 2.5 minutes remaining. Their first run the other day, this robot had some issues. There was some mobility issues. The tracks were doing some weird things, but today on run 2, their final attempt, these tracks have not done anything weird. Their digger has been very productive. Is that duct tape on this? That's duct tape on that front motor. And you can see it moving back and forth. So this robot has been patched together by this team, and it's holding. The duct tape is holding Virginia Tech. Great job. 1.5 minutes remaining. Are they going to load up to the max and make this their final trip to the scoring zone? They're basically lined up with it, with that shortcut there. So they can basically wait till the last possible second that they feel is safe. Now that I see this angle, that motor that's duct taped is kind of like wagging back and forth every time it changes direction. I'm so glad that thing is holding. Yeah, they're loading up. We got 50 seconds. They are loading this thing up more than it has ever been loaded before. I hope their motors are strong enough to even lift that onboard hopper right now. So 40 seconds left for Virginia Tech. This is likely going to be their last deposit into the scoring zone, and their motor appears to be strong enough to lift it. And so out comes the material. Oh, that's a good view right there. Look at that. They're shaking their robot. They know it needs a little help for that material to come out. And in the last 10 seconds of their run, let's give Virginia Tech a big round of applause. They have done really amazingly in their second and final run. They found a shortcut, which saved them a lot of time. And they took a chance, but it worked out for them. Great job, Virginia Tech. You should be very proud of what you've done. Coming up next is going to be, let me check the time. All right. I suspect we're going to run, somebody will correct me if I'm wrong, I suspect we're going to run San Diego State. Are they out in the hallway? Oh. No, we're not going to run San Diego State. We must be taking lunch now because their robot is still in their pit. So I'm going to predict that we will take an early lunch today, and then after lunch we will run San Diego State and Iowa State. And don't forget, everybody in the room, during our lunch break, we will go up on stage and we will give out the Robot Innovation Award. So don't go anywhere. You are watching NASA's 2026 Lunabotics Robotic Construction Competition, streaming live from NASA's Kennedy Space Center. Don't go anywhere. You don't want to miss it.
It starts with a spark that inspires possibilities, a spark that ignites progress. For a century, Caterpillar has been that spark, powering progress across roads, cities, industries, and economies. Together, we've built the foundation of the modern world. But as the world accelerates at an exponential pace, our customers face new challenges every day. Understanding their needs fuels our purpose. We build a better, more sustainable world. To do that, we must listen, develop, and deliver tailored products and services that drive real outcomes. And those outcomes are just the beginning, because sparking transformation means more than building equipment. It's getting closer to our customers without losing focus on creating quality products. It's leading the industry with differentiated digital and technology solutions and embracing new ways of working to accelerate innovation. Ultimately, it's about solving our customers' toughest challenges because the future demands it. We've honored our first 100 years and the strength of the legacy that propels us forward. This is our moment, with technology at the forefront, customers at the center, and our people leading the way. The future belongs to us. Tomorrow takes courage. Tomorrow takes commitment and a spark to ignite it. Tomorrow takes Caterpillar.
250 years ago, 13 colonies laid the foundation for the greatest and most enduring democracy in the history of the world. One driven by courage, faith, and freedom. From that moment, we became a nation defined not by where we stood, but by how far we were willing to go. We conquered vast frontiers, invented tools that shaped a modern world. We found light in the dark, and we rose from the earth. Faster, higher, farther. We pushed beyond the sky and into the unknown. We carried our courage into the cosmos, and we planted the American flag on the moon, the defining achievement of American superiority in space. Today, our curiosity stretches farther than ever. American robots search ancient rivers on Mars. New telescopes unfold to glimpse the first stars. And a new generation prepares to return to the moon, this time to stay. For 250 years, America has carried the light of humanity forward. But American exceptionalism isn't inherited, it's earned. Our greatness comes not only from what we've done, but what we're still determined to discover. Because in every era, across every horizon, America is at its best when it's reaching for something greater. America celebrates 250 years, and we are leading the world into the future.
Taking their first steps outside for their historic test flight.
4 brave explorers ready to ride the most powerful rocket NASA has ever launched.
Reed, Victor, Christina, and Jeremy.
We are going for our families.
We are going for our teammates.
We are going for all humanity.
Engines lit. 4, 3, 2, 1. Booster ignition. And liftoff. The crew of Artemis 2 now bound for the moon.
integrity. Great view.
This is a test flight, and so every single system aboard Orion is getting tested by humans for the first time. That is Earth in the center of your screen from the Orion spacecraft, looking back at all of us.
Houston is go for TLI. With this bird to the moon, we do not leave Earth. We choose it.
The four of us have looked at this moon our entire lives, and the way we are responding to what we are seeing out the window, it's just like we're a bunch of little kids up here. We cannot get enough of this.
That is something we have never seen before.
It's hard to wrap your mind around. Like, I mean that sincerely. It really bends your mind.
As we prepare to go out of radio communication, to all of you down there on Earth and around Earth, we love you from the moon. Just seeing Tycho, there's mountains to the north. You can see Copernicus, Rainier Gamma. It's just everything from the training, but in 3 dimension and absolutely unbelievable.
Kathy Moonjoy. Superlative thumbs up.
We just went sci-fi.
I think there is enough for all. The purpose of humanity is joy and lifting one another up, creating together.
This is a whole bunch of nothing, this thing we call the universe. You have this oasis, this beautiful place that we get to exist together.
Well, I'll tell you, I mean, after ignition, to me, the moment that I'm going to be most excited for is splashdown. There's no question about that. Good shoots coming down off the West Coast.
And there go the first series of parachutes.
And Houston, we're visual 2 drones out the window.
Main chute deployed.
We most importantly choose this moment to challenge this generation and in the next to make sure this record is not long-lived.
This is a relay race.
It takes an army to pull a mission together like this, right? Across all 10 of our centers, all of our commercial partners, the international partners that come together to make this possible.
I became aware of Caterpillar at the NASA robotic mining competition. NASA has a goal to colonize the moon and Mars. So to facilitate a lot of those activities, you've got to be able to excavate the material. So as a way to crowdsource some of the ideas for how to build those excavators, NASA's created this robotic mining competition that Caterpillar is a big part of. Every single year we build this basically a robotic excavator, much like some of this stuff. I mean, we built a front end loader similar to that one year, and you pretty much have, like, I think they give you like 10 minutes and you go up and down the track and you mine and you bring it back and they score you. So autonomy is the big part of the competition now. In the past years, it's been all about, you know, being able to move in the material. The material is something very difficult to work in. But as teams have evolved, the competition has evolved, and autonomy is a key part of that now. And I think that's really one thing that sets our school apart. That's why we do so well. We have an edge on that autonomy perspective. So I think that's kind of what CAT's interested in us, honestly. Robotics is a new way to solve problems. So there's infinite possibilities to solve those problems, and you have a chance to make the world a better place. Honestly, you're developing technologies that make everyone's life easier. You're automating tasks. You're just making a better quality of life for everyone. I normally associated CAT with just this big, large construction type company, and it's really more of a tech company. Now getting to be inside and seeing all the innovative things that CAT does is I don't think people really appreciate all the technology that goes into CAT equipment. Kind of expected it to be a little bit of intimidating, honestly. You know, CAT engineers, you know, but it's a really fun work environment. I love coming to work every day, honestly. Caterpillar has a lot of opportunities to succeed. One of the things that's really stuck out to me that I've learned during my time as an intern, just all the opportunities within the company. I'm a kind of guy that likes to jump around. It's become apparent to me that within Caterpillar, if you want to have an entire career at Caterpillar, you have an opportunity to do all those different things and still stay within the company. You don't necessarily have to leave and hop jobs and things like that. All those opportunities are provided to you within the company. I would absolutely recommend the Caterpillar intern program to my peers. It has been a great learning experience that I'm very thankful for.
Artemis 2 is NASA's mission to the moon, launching in early 2026. It'll be the first time that humans have visited the moon in over 50 years, but it's more like a test flight. 4 astronauts will fly to the far side of the moon on a 10-day journey using the most powerful manned rocket to date. Today, I'm going to break down Artemis 2 for you in 3 parts: the spacecraft, the mission, and the crew. So let's go. Before we get to the mission, I want to explain the Artemis 2 spacecraft real quick. So the whole rocket that they're using is called the Space Launch System, or usually just called the SLS. It has 2 solid rocket boosters on both sides, a lot like the Space Shuttle, and an orange core stage in the middle. On Artemis 2, the solid rocket boosters have something that make them really unique. They have a giant America 250 logo painted on top of both of them to celebrate the 250th anniversary of the United States of America, which is in 2026. Pretty cool, especially considering that this rocket was made by engineers from every state in the United States. The next rocket stage is called the Interim Cryogenic Propulsion Stage, or ICPS. Above that is the upper stage, Orion. Orion is really the star of this rocket, and it has a few major sections too. This bottom section is the European Service Module, or ESM, and it provides power and propulsion. It's the way that Orion gets around in space. Then there's the crew module, sometimes called the capsule, and this is where the astronauts live and work. In fact, astronauts will stay in this capsule the entire mission. On Artemis 2, the crew have named their capsule Integrity. When the entire mission is done, this capsule is the only part that will return back to Earth. And finally, this top tower bit is called the Launch Abort System, or LAS. Hopefully the astronauts won't need it, but if they do, it can actually pull the capsule away from the rest of the rocket if there was a major malfunction or an explosion, and hopefully save the astronauts' lives. If you want to learn more about the SLS, I have a whole video about that right here. Now that we know our spacecraft, let's talk about the Artemis 2 mission specifically. As I mentioned before, Artemis 2 is a test mission. Artemis 1, the first test of the Space Launch System, it launched back in 2022 and was an amazing success. But Artemis 1 was uncrewed. Now it's time to test this full system with crew on board. And this crew is going to be able to test out a lot more of the human-centric features. Docking, radiation shielding, communication, eating.
The four of us will gather to share meals when we're on our 9-day trip around the moon. Inside here, our device will be able to portion out water to fill up water bags for us to drink, but also to rehydrate the food.
Sleeping, exercise.
This is the flywheel device. And what I kind of want you to imagine is a rowing machine. So we can do rowing like a cardiovascular workout, can do weightlifting with it. So we can do squats, we can do deadlifts, we can do curls, varied levels of resistance to really put a lot of stress on our muscles and our bones.
Going to the bathroom.
Inside the capsule, this would be the floor. You would float over to it, open up this hinging door, float on in.
All the human things that we couldn't test before. Artemis 2 will launch from the Kennedy Space Center in Florida from Launch Pad 39B. Launch Pad 39B launched Apollo 10 to the moon in the 1960s and many shuttle missions, including this shuttle mission that I got to see launch when I was a kid. And it will launch as early as February 5th, 2026. And when the countdown hits 0, it's going to be the most powerful manned rocket launch in history. 2 minutes into launch, we're going to jettison the solid rocket boosters and be left just with the core stage powering it into low Earth orbit. And this is when the launch abort system will be jettisoned as well. 8 minutes in, the core stage is out of fuel, and so it's going to separate and fall back to Earth, while the second stage, the ICPS, ignites and gives the final push to get the crew into space. After 2 burns, the ICPS is going to have Orion in an elliptical high Earth orbit. And so now Orion is going to be 46,000 miles away from Earth on the far side, and the close side of its orbit is going to be 115 miles from Earth. And this orbit will take about 1 day to complete. During this first day, Orion's going to separate from the ICPS and begin to do a docking practice maneuver. In the coming years, Orion will dock with the lunar lander and the Gateway station. So we need to know, how well does the autopilot work? Do the thrusters work the way we expect them to? If you remember the 2 astronauts who were stuck in space for a while, Butch and Sunny, last year, they were testing out a new spacecraft called Starliner. And the whole reason that NASA kept them on the space station for months instead of weeks was because of bad thrusters. We need to make sure Orion does not have similar issues. Once Orion passes back by the Earth, it's going to reignite its engine for the translunar injection, or TLI. This is the final push to get our astronauts to the moon for a free return trajectory. What is a free return trajectory, you may ask? It means the gravity of the moon and the Earth will naturally bring Artemis 2 back home. No additional burns required. This is a great idea for a test spacecraft like Orion. If anything goes wrong with Artemis 2, it'll just naturally come back to Earth using gravity alone. This is actually the same flight path that ended up saving the Apollo 13 astronauts after their disaster on the way to the moon. For Artemis 2, the journey to the moon is going to take 4 days. During that time, the crew is going to be running emergency procedures, including what to do in case of a major radiation event. See, if humans are going to do these long missions that we're talking about, like going to the moon or maybe one day going to Mars, we have to figure out how to deal with deep space radiation. Orion has a shelter on board, and the astronauts are going to test and see how effective it is in actual use. All right, so as I mentioned before, Artemis 2 is not a lunar landing. The astronauts are not going to be walking on the moon for this mission. This is a lunar flyby mission. If you're at all familiar with the Apollo 8 mission from the 1960s, that's the Christmas Apollo flight, this mission is really similar. Their flight is going to take them 230,000 miles away from the Earth to the far side of the moon. As you may already know, there's a side of the moon that always faces the Earth, and then there's a far side of the moon that we will never see from standing on the Earth's surface. And that's the destination for our Artemis 2 astronauts. This is a simulation of what that flyby mission for Artemis 2 is going to look like. This is actually what the astronauts will see. The closest the astronauts will get to the lunar surface is about 4,600 miles. After the flyby, Orion will do any necessary little corrections that it needs to land precisely at the right place and the right time back on Earth. After another 4 days, Integrity will separate from the ESM and re-enter the atmosphere for splashdown. They will splash down in the Pacific Ocean, be picked up by the United States Navy, and complete their 10-day mission. All right, so let's talk about the crew. There are 4 astronauts on board Artemis 2: Reed Wiseman, Victor Glover, Christina Cook, and Jeremy Hansen. As you might guess, these 4 people are exceptional, some of the best, the exact people you would pick on an Artemis 2 mission. I'm going to highlight just a couple of things that stood out to me about each one of their bios, but seriously, you need to go read them. I've linked them all in the description of this video. These are incredible people who have done amazing things in their lifetimes. Reed Wiseman will serve as the commander for Artemis 2. He is a 27-year Navy veteran, a pilot, a father, an engineer, and a Baltimore native. Wiseman has been an astronaut since 2009, and he's logged 167 days in space. Victor Glover will be the pilot for Artemis 2. He's a test pilot, a legislative fellow with the United States Senate, a father, and an engineer from California. He served in Operation Iraqi Freedom and has flown 40 aircraft across 24 different combat missions. And Glover has been an astronaut since 2013. Christina Cook is a mission specialist on Artemis 2. She's an electrical engineer, an Antarctic explorer, a firefighter, and has worked on major scientific programs for both NASA and NOAA. She grew up on a family farm in Michigan and attended North Carolina State University. She's been an astronaut since 2013 and holds the record as the woman with the longest single space flight, almost a full year. And finally, we have Jeremy Hansen. Hansen is a Canadian astronaut, and he will be a mission specialist for Artemis 2. He's a pilot, a physicist, a colonel with the Canadian military, an aquanaut, and a father. He first got his wings when he was just 16 years old and became a firefighter pilot for the Royal Canadian Air Force. He became a CSA astronaut in 2009, and in 2017, he became the first Canadian astronaut to lead a NASA astronaut class. And get this, Artemis 2 is going to be Hansen's first space flight. You can't really beat a trip to the moon as your first flight in space. So that's the crew. 4 incredible astronauts who are going to be able to test out everything for future missions and be our first return to the moon in over 5 decades. So the big question, when is Artemis 2 happening? Very soon. The first launch window for Artemis 2 opens on February 5th, 2026. Now, it took Artemis 1 a couple of launch attempts before NASA got everything working properly. But the result of that attention to detail and that patience was a very successful flight. And this time, Artemis 2 has actual humans on board, so don't be surprised if there are a couple of scrubbed launch attempts over the next couple months. Me and my family are hoping to be there for launch, hopefully with some of you guys. And if you are as excited for the Artemis 2 launch as I am, be sure to check out all of the Artemis 2 shirts and merch that I have put out on my Digital Astronaut Etsy shop, like this one, available now. Be sure to like and subscribe, and you can check out my other Artemis videos right here.
Hello. Come down to this end of the room if you're not already here. We're about to do a little mini award ceremony. And now, yeah, that's what I'm talking about. And now here's a man that needs no introduction, Mr. Rob Mueller.
Did you have a good time so far? Yeah. Good. It's all about working hard, but it's also about playing hard. And it's also about innovation. So what I'm going to present now is the Innovation Award. And the Innovation Award goes to one team. It's just one team, and it's based on doing something different, something that's never been done before. And we've had several teams this year that did things that weren't done before. There was a team that had auger wheels back in the qualification rounds. They drove on augers, and it was really interesting, very innovative, but they're not in the final. So it has to be innovative, but it also has to be useful. So innovation is great, but innovation that doesn't work is not useful. So that's the basic criteria for this award. The way we do it is we ask all the judges to walk around and look at the robots, watch them compete, and talk to the teams. And it's informal. They just walk around. You might not even know that they're judging you while they're talking to you or watching you, but they are. And then the last day, today, we get all the judges together and we say, okay, who wants to nominate a team for the Innovation Award? Then we put the nominations on a whiteboard, and then we vote on which was the winner. So that's the process. This competition is about you. We want you to be a good systems engineer. We want you to be a robot designer. We want you to be a good robot operator. We want you to have 21st century skills in your toolbox. So it's all about you. But it's also about us. We want to learn something from you, and we want to see what sometimes when you're in an organization you get locked into thinking a certain way, and it becomes a little bit of an echo chamber. And so we want to make sure we don't become a victim of our own echo chamber, and that's where you bring so much value, because you all come from different places, different backgrounds, very diverse, different perspectives. So that's valuable because you might see something that we don't see. And we have about 50 teams that come to this competition every year. And that's a lot of different ideas, different robot designs. We want to crowdsource the thinking. We want to make sure we're not a victim of groupthink. And that's what the Innovation Prize is about, is maybe you saw something that we didn't see. And maybe you innovated in a way that we hadn't thought of. And that's the spirit of the Innovation Prize. So that actually happened this year. We have been watching everybody, and there's some really cool things out there, like measuring the level of the regolith with LED lights. That was very interesting. And those innovative wheels we talked about, and then some details on your designs. I've been looking closely at the wheels. Just designing the wheel by itself is difficult, right? There's so many options. Do you have big wheels? Do you have small wheels, wide wheels, narrow wheels? Do you have grousers, big grousers, small grousers? How many grousers? Do you have curved wheels that are flat? Do you have concave wheels? Do you have convex wheels? Lots of different things you can do. So just the wheel itself is an innovation. We've been looking at that. But this year, we found that one team took something which we thought we knew very, very well and did something new. So that is why this team won the Innovation Prize. And so we'll get this plaque. The plaque is empty because it gets engraved. So we're going to engrave this and send it to the winner. This year's winner, because of what they did in innovating a mechanism, an excavation mechanism, we decided they were worthy of the Innovation Prize. This year's winner is the University of Virginia. Come on up. But I want to explain why they're the winner. First of all, they took something which we have done, which is the IPEX bucket drum. Some people said, University of Virginia didn't innovate. They copied a NASA design with a double bucket drum excavator. And I agree, that's not innovation. They copied our design. But we want you to do that because we'll learn from it. But what they did different than us is they took the bucket drum and they reimagined the bucket drum, and instead of having lots of little scoops on it, which are in a helix, they turned those little scoops into a curved helix, which is the cutting edge of a blade. And it's very difficult to manufacture. To be honest, one of the reasons why we didn't do that is it's hard to manufacture. So we took more of a manufacturing approach of what can we manufacture and realistically what will survive. So even though you did that and you 3D printed it, we still need to figure out how to do that in a way that will survive on the moon, right? Like the plastic 3D printing will not survive on the moon. But still, it's cool. And it's different. And that was reason number one why they were given the Innovation Prize, because they reimagined something that has been very, very well studied by NASA. So let's have a round of applause for that. The second thing they did is they failed. They failed badly. The wheel broke. And they had no wheel, but they kept going. They kept competing with 3 wheels. And not only did they compete with 3 wheels, they actually were berm building with 3 wheels. So that shows how robust this design is. So that's reason number 2 for why you won the Innovation Prize. It was you had a good design. Operationally, you were innovative. You kept going. A lot of teams would say, we failed, stop. You said, hell no, we're not stopping. We're going to keep going. So that's an innovation. It's an operational innovation. So round of applause for that, reason number 2. Reason number 3 is I talked to the mission control judges and said, those guys were having a really good time. And I was like, what? They broke? Their wheel broke and they were having a good time? They said they were laughing about it. And they wore silly hats. And they were having a good time, because when you have a good time, you're relaxed, and when you're relaxed, you perform better. So that's innovation number 3, is being relaxed and having a good attitude and having good team spirit. So it's all about teamwork, really, this competition, systems engineering and teamwork. But that was reason number 3. So applause for that. And if I can have the team captain or team lead step up. Who is that? Okay. The 2026 Lunabotics Innovation Award goes to the University of Virginia, and we'll take a photo. Okay, let's stand over here.
Wait, I think you're definitely part of this. Ryan.
Yes.
Yeah.
Thank you very much, and don't remember, we have the award ceremony this afternoon. I see a lot of people packing up. Don't leave. Thank you.
Thank you.
Congratulations, well deserved. All right, finish up your lunch break. And then at 1 p.m., top of the hour, we should see San Diego State University run. And then at 3 p.m. or 2 p.m., we should see Iowa State run. So, and then at 4:30 p.m., unless somebody corrects me, the award ceremony is planning on occurring. So 2 more runs at 1 and 2, and then 4:30, a final award ceremony. Thank you. Don't go anywhere. You don't want to miss the rest of Lunabotics 2026. You are watching NASA's Lunabotics 2026 Finals Competition, broadcasting live from Kennedy Space Center's Visitor Complex. What you're seeing on the screen right now is a robot, San Diego State University's robot. This robot is about to simulate that it is operating on the moon. And what it will be trying to do on the moon is to dig as much moon dirt as it can in a 20-minute competition run and cross over an obstacle zone with that moon dirt, and then deposit that moon dirt in another corner of our simulated lunar surface into a scoring zone. So essentially, the more moon dirt a team's robot piles up in the corner of our arena, the better. I should mention that the students who will be monitoring and controlling this robot are in a completely different room. They are in a mission control room way on the other side of the building. They cannot directly see the robot. If they choose, they will be able to see one or two camera views that are supplied by NASA. If they choose to use those camera views, though, there will be a point penalty. A lot of teams choose to use only their onboard cameras in order to avoid that point penalty. You can see this San Diego State University team here in our mission control room have at least 3 laptops in front of them, 3 screens in front of them full of data. And when this competition run starts, one or both of those NASA, those other monitors on the left that you see may get turned around if the student team has decided not to use those. Those would be the NASA supplied video feeds. Both of those NASA supplied feeds are basically overhead cameras. One of them is stationary and not movable. The other one is a pan tilt zoom camera that the students can control if they desire to take that point penalty. You can see a timer on the screen, just under a minute left in the setup time for the San Diego State University team. Once that timer runs out, our judges will verify that we are ready to go, and they will start a 20-minute timer for this competition event. This is the second of 2 official competition runs for San Diego State University. On the screen, we are essentially looking at the back of the robot, I would presume, the front of the robot being the digging end, and the back of the robot being the delivery end. So the digging end of this robot is a wide conveyor belt that spins around, and it has these metal triangle-shaped pieces of metal on it that are essentially scoops that will scoop up this moon dirt. And it will dump the moon dirt into an onboard hopper, which has a conveyor belt that will move that onboard material out of the way and make room for more. All right, the students from San Diego have left the arena, and now we have some judges that are looking over the robot and doing their last checks and writing down some numbers that are being displayed on the robot. And as soon as those judges are finished, we should see a 20-minute timer, and we should start this run for San Diego State. This is a very big robot that this team has brought to our competition. This robot is about as big and about as heavy as is allowed in this competition. And the students are made that decision on purpose, and they're betting that maximizing is going to be the thing that gets them the win here this week in Lunabotics 2026 finals. Now the 20-minute timer has started, and looks like the robot is going to dig right there where it starts. And this is a great angle of the digging. You can see this bucket ladder conveyor system spinning around. You can see the bottom where the scoops are getting little bites of simulated lunar soil. And you can see at the top where they are dumping, these scoops are dumping into the onboard hopper. I can see in the control room students' hands on joysticks, so I suspect this is a manual digging operation. Only the mission control judge knows for sure. 1 minute in, the bucket ladder system has raised a little bit, which means we're no longer bringing in material. And then the robot backed up a little bit. I don't think the digger is raised up all the way. Okay, now it's plunging down again. Driving down slowly into this crushed volcanic rock, which simulates our moon dirt. And this crushed volcanic rock is very small particles and very jagged particles, which makes them not terribly easy to dig in. This is a great view showing the onboard hopper filling up and the conveyor belt moving. Oops, they don't probably want to dump out the backside quite yet, because that won't count. It only counts if you deposit material into the scoring zone, otherwise known as the construction zone. You can see the digger raising up slowly and the camera turning around into driving mode. So the camera was just earlier turned back to look into the robot's hopper. But for driving, the camera swivels and looks at where the robot is going. So dual use for that camera. That saves on weight. Also saves on bandwidth, both of which are being monitored and judged as part of this event. I still see hands on joysticks, so this is very likely manually driven. Although there's a non-zero chance that the student is using the joystick to turn on or activate certain autonomous operations. So just because I say, I think this is autonomous or I think this is manual, that is just a presumption on my part. Only the judges know for sure. Looks like they're going to dig in a new spot. That last dig, you can see the little trench that that was made by that dig just now in the upper right of the screen. It started out plunging straight down and went reasonably deep, and then lifted up and just kind of scraped the top surface there while the robot drove backwards. Students are typing on the keyboard. Something may have happened on board the robot that needed to be fixed. All right, looks like we're back in business now. Oh, they are going to turn and go back to that spot that they dug in before. All right, they're going to dig right there. No, it came back up. I'm watching for the front-mounted bucket ladder to go down. I'm fairly certain the student is stick driving this robot right now. Teams have the option to manually drive the robot or to activate certain autonomy modes. Okay, this is actually digging uphill right here. So the fact that it's working so well is impressive on non-flat, non-level terrain. Looks like they're digging shifted to the right from where they had dug prior. A lot of teams you'll see never dig in the same spot twice in order to keep from digging really, really deep trenches that you might get your wheels stuck in later. This is a problem that robotics engineers need to think about and plan their missions. So Lunabotics prepares these students in a lot of different ways for future work in this area on lunar robots. Looks like the students are filling up the hopper now. The conveyor belt has moved back, but looks like they're maximizing this this part of the conveyor belt right up to the buckets. Okay. Now we're going to drive. That looks like a nice load on board to me. And when we see it dump, it looks like a lot. All right, the team's got to be happy with that. 12.5 minutes left. This team should be able to get several more cycles of that. So, saw some more typing on the keyboard just then. Something may have gotten stuck somewhere, software-wise or process-wise, but the students are on it and are able to fix and correct in real time from the command line. All right. Where are they going to dig this time? Looks like they're backing into a position towards the wall. Shifted to the left. The robot's left, our right. The robot's right, our left. And that's where they're going to start digging. And then they will probably drive towards the camera as they dig. You can see one of those wheels is in midair because one of the front wheels is in a trench that they had dug earlier. This is something that happens in robotics when you are working on uneven terrain. And now the back wheel is in that trench, lifting up the front wheel. But the students can recover from that by changing the pointing angle of the robot or just driving to a different spot. So now they've driven forward. And now they're digging quite deeply right there. They're pointing downhill, probably deeper than they wanted, so they're raising it. Not sure why they shifted left there, because the front wheel's about to drop down into a hole. They're digging deep right there. I don't know if they're stopping that digging on purpose. Yeah, I believe they did. I can see students in the control room telling the driver student where to point the robot and where to drive the robot. So they're adjusting in real time based on the conditions that they see on the camera that NASA's providing this team. It looks like it's time to deliver this load. Of course, the robot needs to back in, so there's going to have to be a little bit of a turnaround maneuver here, which is going to take precious time in their 20-minute run. We're under 9 minutes remaining for San Diego State. Looks like they're in scoring position now, and there goes the conveyor belt. Very nice. All right, time to go get some more. Under 8 minutes remain for San Diego State University. They're going back to that spot that they had dug in before, which has some trenches that makes it a little hard to drive in that area. All right, we're at productive digging depth. You can see the whole robot shaking a little bit as they hit harder areas. They could be hitting rocks occasionally. They could be hitting just more compacted areas of this crushed volcanic rock, which makes up our lunar simulant. They just dumped a little bit out the back. A lot of that dig was uphill And I'm not sure that they were as deep as they wanted to be. Under 6 minutes for San Diego State. They may be trying to find the best spot to dig in an arena that is far from perfectly flat. If any of these teams assumed that our arena would be perfectly flat, they are getting a surprise when they compete here this week. All right, with under 5 minutes to go, looks like San Diego State is making another trip to the construction zone, which is where they deliver the material. Which should give them time to do one more cycle before the timer runs out. This is going to have to be a quickie though. And they're digging. 3.5 minutes to go. So they can probably dig for about I was going to say 3 minutes, but I'm not sure if 30 seconds is enough time for them to perform their delivery operation. Three minutes left. Those are really overflowing buckets. Those are really good bites right there when they push their robot into that forward, into that trench that they're digging. They're getting really, really full bucket loads coming around. Raising their digger. They may be heading back over to the scoring zone now, because that was a very productive dig session. Two minutes left. That's a lot. Each one of those deliveries look like a nice sized pile. So I imagine this team is happy with the performance of this robot. Will it be enough to win a prize in our award ceremony later this afternoon? All right, they're going back. They only have a minute left. If they're going to do another cycle, they need to hurry. "40 seconds. Digger is not touching the ground. So this has not been productive so far at all. It's got a little bit there. 30 seconds. They may be trying to go back, but they've only got 20 seconds. And things got really soft right there. 10 seconds. Their digger is dragging behind them. They're just not going to make it back to the scoring zone. Let's give San Diego State University a big round of applause. Great job. That was fun to watch. Impressive robot there. All right, coming up next is our final run of the day, final run of this entire Lunabotics finals event here at the Kennedy Space Center Visitor Complex. We have Iowa State coming up next. They're excited. The robot is getting ready to go into the arena, and you can see the Iowa State students all suited up, ready to go into the arena and place their robot into the competition arena for their final run. So don't go anywhere. You don't want to miss our final competition run here at 2026 Lunabotics competition. You're watching NASA's 2026 Lunabotics Finals event, streaming live from NASA's Kennedy Space Center Visitor Complex. The Iowa State University robot has just started its second and final competition run of this competition. And this is the last of our 10 teams to compete. So you were watching the last run of our event this year. This robot presumably just did, yeah, I just saw the student pick up the joystick. That was an automated dig event, and now I think, so the students probably got credit for that automated dig, and now they may be probably doing a manual dig. So the students will get extra points for having some automation there. And each team chooses what parts of their operation they want to perform autonomously and what portions they want to just maximize their throughput and just drive as hard as they can in order to maximize the amount of material that they deliver. This team, when you see a robot stop like that, sometimes they're configuring something or about to activate a new mode. For example, an automated traversal, which is what I think is happening right now. The student hit a button and then put the joystick down, and then the robot started spinning. So this spinning is usually an indication of a mapping routine. The robot's sensor needs to, oh, okay, that was a little worrisome. I thought it was going to hit the wall. The robot needs to show its sensor to the entire arena in order to map it out. And it looks like the students took over control because the robot was hitting a rock there. So this is a manual drive. Are they going to drive over those rocks just like that other team did? Or are they resetting in order to try another? Nope, all of that effort was just to turn this robot around. It's a pretty big robot, and just needed a big space to turn around. No, I think they're going to set up for another autonomous traversal. Even though this is going to eat up some precious time, if it succeeds, the autonomy points are going to be worth the effort. All right, I think the students are just stick driving it because too much time was being wasted on their autonomy attempt. So the robot needs to back in to the scoring zone in order to be in the correct spot. Okay, I think they're setting up for an autonomous delivery. Yeah, the student is showing the joystick to the judge, hitting a button, and then putting the joystick down. That's what just happened. So this is autonomous. Students are getting some bonus points for doing this operation hands-free. So 5 minutes has expired. What I expect will likely happens a lot for a lot of teams, is that they try a couple things in autonomy to get those points, and then the rest of their time is spent running manually because their production rates are so much higher when they're running in manual mode. And yes, the student is holding the joystick still, so this is very likely a manual dig operation. This robot lowers its bucket ladder digging system into the soil and then drives forward in order to dig fairly wide, and that's a couple inches deep, I would say, trench. That is a respectable trench. Now later, if this robot gets one of its tracks in that trench, hopefully that doesn't cause them any problems driving. I would say they have quite a bit. It's really hard to see because of the covers on this robot, but I would say that this Iowa State robot has a lot of material on board right now. We'll get to see how large of a pile gets deposited right here. Again, this appears to be manual driving. It's a nice big pile there. All right, so that only took 2 minutes, what we just saw. So if they do that 6 more times in the last 12 minutes, they will, I think, be really happy with their score. So they started way back against this wall, and they're driving towards the opposite wall, basically using almost the entire length of the digging zone. Okay, they're crossing over their old trench. I wonder how that's going to work with the productivity and the tracks dropping into the old trench right about now. That's going to make their digger go deeper. And so they raised up a little bit and compensated. So that didn't cause any problems with this robot. It didn't look like. There's some big rocks that they just brought up to the surface just then. This robot is not turning around in the middle of its run. It's digging on the front end of the robot and dumping from the rear end of the robot and making just a single arc between the two, not having to waste time to turn around. And it appears to be working for them. 11 minutes left. So at 2 minutes per cycle, okay, they're turning the robot around. They're starting in the opposite side. Spent a little bit of time to turn the robot around. Now they're going to drive in the opposite, dig in the opposite direction than they did earlier. Now they're going downhill, which means their digger's probably going to get a little deeper. I think that's the depth that they are wanting. Now that it's not going downhill, they might have to adjust the height of their digger a little bit. You can see it pushing rocks that are just not sized to fit in their system. If they didn't push those rocks out of the way, I fear that they might jam up this system. Oh, they're digging some more. They're not full yet. This team appears to be maximizing their onboard hopper because they could have gone and delivered just then. Okay, so now the robot is turned around, only having to do a 90-degree turn, not a 180-degree turn, in order to face the direction needed for depositing this material into the scoring zone. That is a lot of material. That is a lot of material. -90-degree turn. Another 90-degree turn. You can see they're taking a slightly different path than they had earlier. They're crisscrossing their own digging path. Explicitly not digging in the exact same trench more than once. All right, are they full? Nope, they're gonna dig some more. Just need a hair more on board, I think. 7.5 minutes remain. Oh. We had a failure of their, their digging system got caught up in something and did some damage. Let's focus on depositing this material into the scoring zone with just under 7 minutes remaining, and then we can focus on the digger. That looked like a really bad day for that digger, though. Oh, I wish I had another camera angle. Oh, man. I think they're going for it. I think it was, they do have some buckets that are torn up, and they were getting caught in the pieces parts that are covering their bucket ladder system. I think they're just trying to tear away that plastic and that red fabric to get to a point where they can just have a free bucket ladder system. But I believe some of the buckets have torn off and are probably clogging up the works. That was a valiant effort, though, to just go for it and just rip off whatever rips off. And if it still works, then go for it. It appears, though, that in going for ripping things off, some things got damaged that may be unrecoverable. You can see how many buckets have been ripped off just on the front of this robot, and then ones that are on the other side of the conveyor belt are probably jamming up the works and keeping this robot from being able to move. Yeah, it looks like the students decided to just call it because there's no way to recover from this. Camera 4 has another angle. Of the damage. You can see that belt is actually in an area that maybe it shouldn't be in. Buckets are jammed and squished and squeezed, and I really do appreciate the effort that the students took to just run it at full speed and see if they could rip off the stuff that was in the way and continue. So after all of that, camera 1 has a side view of the berm that this Iowa State team has created. Kind of in the upper right, you can see how big that berm is that they created. I'm going to say it out loud. That is a big berm. So I'm just going to say it. Even though this team had this failure and lost, what did they lose? Like 5 minutes out of their event. I'm going to say they should still have hope. This berm they created is impressive. So I hope the students are not too sad or mad about what happened to the robot in that event. They should feel very proud of what the robot accomplished in, 15 minutes? Because they still had 5 minutes left on that 20-minute run when that failure happened. So I feel like this Iowa State team should feel very proud, and I don't know. I'm going to be interested to find out where they end up in the scoring, because I'm impressed with this berm, even with the short period of time that they were able to operate. All right, with that Iowa State event complete, let's give Iowa State a big round of applause. What a great effort on their final run. They had a bad failure. I mean a blowout. that was an amazing thing to see that robot tear itself apart there at the end. But man, that team should feel really good about what they just did. And so looking ahead, that was our final run. It is now 2:30 in the afternoon. What happens at 4:30 is our award ceremony. We're going to have our award ceremony in 2 hours from now. We're going to have it right here in this end of the room where we had our opening ceremony and our other mini award ceremonies. So this gives teams some time to pack up if they want to, and get all, maybe get a snack if they had to rush through lunch and didn't get a good lunch, and come back all rested and excited for the award ceremony at 4:30. This also gives our judging team a chance to fully complete their entire process, make sure all their T's are crossed and their I's are dotted, and give them plenty of time to have all of their meetings and their sub-meetings and their meetings about other meetings, and make sure they are completely sure about the result and not be rushed. So we do have a 2-hour break. Our live stream is going to just continue during this 2-hour break so that we don't have to send out a new URL for just the award ceremony. We want everybody to have the same URL. So bear with us for the next couple of hours. Live stream might look a little boring here and there, but we'll try and throw up some videos occasionally for entertainment and for education, obviously. So I'm not going to say don't go anywhere. Feel free to go somewhere, but come back in 2 hours, both here in the room and online. Come back in 2 hours. Award ceremony happens promptly at 4:30 p.m. Eastern. You're watching NASA 2026 Lunabotics competition here at NASA's Kennedy Space Center Visitor Complex. We see the students on the screen. They're now seeing the wreckage of their robot. Those poor students. 4:30. See you then. Hello, hello. Hello. We are not starting the award ceremony yet. I just feel bad that you're all here and you're staring at the stage and you're not being entertained. Who wants to hear some robot jokes? What an easy crowd. All right. Did you hear about the robot that got arrested? They charged him with battery. Thank you. You're too kind. You're too kind. Okay, who in the audience has a robot joke? I know. I surprised you with this. Anybody? Anyone? Okay, I'll continue. I'll continue to warm up the crowd with my next joke. But think about it. How do you know when you're in love with a robot? You feel a little spark. Yeah, thank you. Your turn. Who has a robot joke? Do you have one? We have one over here. Okay, hold on. No, wait for the mic. Wait for the mic. Wait for the mic. It can be a space joke.
I want to make this very clear. This is not my joke, and some...
I'm going to interrupt because I want to make sure everybody knows we are live broadcasting this. Anything you say into this mic has to be clean. Do not get a shutdown on YouTube, okay? This is your warning. Continue.
Okay. A NASA employee told me this. Why can't they use Linux in space? Why do they only use Linux in space?
Why do they only use Linux in space? I don't know. Why?
Because you can't open Windows.
Oh, yeah. That's a good one. That's a good one. I cross that one off of my list. Oh, did you hear about the new surgical robot? So far, it's new. So far, it only operates on batteries. Oh, that's okay. You can clap. Your turn. Who's next? Raise your hand. Do you have one? Sounds like you have one.
What do you call a construction robot that fell asleep?
Construction robot. Oh, I heard dozer.
A dozer.
Dozer. Isn't there a rap about? Sorry, I'm reading ahead. Is this a good one or not? I don't get that one. Oh, okay. That one's dumb. Crossing that one off. Why don't robots get scared? They have nerves of steel. I do appreciate the applause. I did find these on the internet, though, so I can't take credit for any of them. Your turn. Okay, we have a volunteer, our very first volunteer. This is so exciting. You weren't voluntold by a neighbor. You actually volunteered yourself.
Why didn't the sun go to college?
Why didn't the sun go to college? Any guesses?
Because it already had 1,000,000 degrees.
Whoa! Good one. I'm getting my steps in. As if I haven't already been standing all day. What is R2-D2 short for? Because he's got little legs.
That's what he's short. That's why he's short. Thank you, thank you. Again, I did not make these up myself. I cannot take credit for any of these. Are you listening to the live stream right now? How does it sound? Thumbs up. Who's next? Raise your hand, big and tall, big and tall.
What's a robot's favorite food?
Favorite food. Any guesses?
Microchips.
Oh! Little bitty chips. Why was the robot so angry? You've all heard this one, right? Because everyone just kept pushing his buttons. A groaner, but still get the clap. Who's next? I need a volunteer. I can't do this all on my own. All right.
What happens to your data if Bigfoot swallows your computer?
If Bigfoot swallows your computer, Bigfoot, he's got big feet, he's hairy. Any guesses? I have no idea.
It's encrypted.
Sorry, I'm a little slow. Okay. I think I got it. That one might have went over my head. I'm sorry. I'm under a lot of stress here, though. Give me a break. That one's too lame. Sorry, I'm not going to say that one out loud. Okay, this is my final robot joke. It's a one-liner. Two robots run into a bar. The third one had a better driver. Wah, wah. Do we have any more? Okay, right here in the front row.
Why did the construction robot have to leave?
Why did the construction robot have to leave? I don't know.
It had to bolt.
Bolt. Get it? All right. That was fun. Guess what's next on my little cheat sheet here for time-killing ideas? NASA and space trivia. Who's excited about NASA and space trivia? Who's excited enough about NASA and space trivia that they will come up here and form a line? I need 4 people to answer NASA and space trivia questions. Come on. First 4 people. We got 1. We got 2. We got 3. Are you volunteering? All right. Awesome. 4 volunteers. 4 volunteers. All right. Raise your hand if you want to answer this question. What does NASA stand for? Okay, I saw your hand first. It may have been because I was looking right at you. I apologize if that's the case. What does NASA stand for?
National Aeronautics and Space Administration.
That is correct. Hold on. Hold your horses. Young man who just answered that question, I have a prize for you. Really? Who knew that there were prizes? This is an Artemis Frisbee that I bought from the NASA gift shop. It's all yours. And now you may sit back down. Open up a slot for one more person, one more volunteer, whoever gets it. I see a hand over here. Come on up. Thank you. Okay, I'm going to stand over here to be a little bit more fair in seeing the hands raised. Who has a guess? Because I'm sure this one's pretty. I mean, how could any of you know this one? What year was NASA officially established in Congress? Yes. What is your guess?
1958?
You knew that. That was not a guess. Sorry, I have to. That was amazing. Who at your age knows the answer to that? Come on. Sorry, I'm organizing so I can actually see what I'm giving out. All right, I have a prize for you. It is a really nice refrigerator sticker. Or you can put it on anything metal. All right, congratulations. Take a seat and open up a spot for the next volunteer. Who wants to go next? Thank you, young man. Come on up, come on up, come on up. Who's coming up? Who's coming up? Who's coming up? Who's coming up? Okay, we'll play with 3. We got to keep things moving here. All righty, your odds are better now. Okay, this is a long question, so listen carefully. What official government organization was in place since 1915 to guide America's aeronautical research and was dissolved and replaced by NASA in 1958? Yeah?
NACA.
That's right. Bonus points if you know what that stands for.
National Advisory Committee on Aeronautics.
Yes! Is somebody out there feeding him answers wirelessly? That was crazy. Am I right? I'm giving you not only an Artemis refrigerator magnet, but I'm also giving you a NASA sticker. That's a NASA worm. All right. Please take your seat. Do we have another volunteer? Come on up. Okay. Everybody listening? Who was the first American in space? Yes.
John Glenn.
Incorrect.
Who's Alan Shepard?
It was Alan Shepard. For that, you get 2 pins, a NASA meatball and a space shuttle pin. Congratulations. Who's next? Come on up. Come on up. And you get another chance. There's no harm. There's no penalty in answering incorrectly in this game. All right, raise your hand if you know the answer to this question. Who was the first American in Earth orbit? Oh, you beat him.
This one's John Glenn.
Yes. Dude, that was your chance. All right. 2 pins, NASA meatball. You don't want another NASA meatball. That would be silly. And Artemis. Great job. Who's up? Who's coming up? Who's coming up? 2 people can. 2 people can. We got room. All right. All right, come on up. Okay, this is another number question. Wait, you can't play more than once. You can't play more than once. Come on, somebody else. Somebody who hasn't already played and won a prize. There you go. Come on up here. Don't be afraid. I don't bite. I can't speak for this guy right here, though. All right. What year did we first land? What's your answer?
1969.
That is exactly what we were going for. What year did we land human explorers on the lunar surface? It was 1969. Okay. Yes, yes. Extra prizes for guessing even before knowing the question, which means you get 3 stickers. You get an Artemis sticker, you get a NASA worm sticker, and you get a very limited edition SwampWorks. Yeah, that's what I'm talking about. Sticker. Congratulations. Okay, one more. We're running out of time. Oh, yeah. This is fun. Okay, everybody ready? Who was the first person to... Okay, we got a guess.
Is it Neil Armstrong?
It is Neil Armstrong! Wow! To step foot on the moon. You nailed it. Okay. That was, okay, by the way, that was my only SwampWorks sticker earlier, so I'm sorry. You get an Artemis sticker and a NASA meatball and a NASA meatball pin. A worm sticker and a meatball pin. Oh boy, I'm getting a little low on prizes here. Okay, no more new people. No more new people. We're working with these 3. Okay. Do any of you know what Jupiter's giant ocean is made out of? That's a tough one. So, okay, you got a guess?
It's going to be hydrogen on Jupiter.
It is hydrogen. It's liquid metallic hydrogen. Okay. Wowzers. These kids are smart. Man. That's a NASA worm sticker. Yeah, buddy. This is not a sticker. It's a temporary tattoo, and it's a NASA meatball. Are you kidding me? Come on. Actual tattoos. All right, we're down to 2. And we got 1 minute until the award ceremony starts. Oh, the drama. What galaxy is our solar system located in? Yes, I saw your arm go first.
That's the Milky Way.
Milky Way, just like the candy bar. Thank you. All right, last but not least. Okay, this is interesting. You've heard of NASA's Deep Space Network? It consists of some large antennas, and they're positioned all around planet Earth. Sound familiar? How many antennas are there in the Deep Space Network? You can ask for help. You can get help from the crowd. You can phone a friend. Okay, guess. Guess. There's no penalty for a wrong answer.
13.
No. Anybody in the crowd know what it is? Yell it out. It's 3. I know. Can you believe that's it? It's like perfectly triangular. Look it up. Look it up. It's crazy. It's perfectly triangular around our circular, our sphere Earth. Crazy. Don't go anywhere. Don't go anywhere. We're going long. We're going to keep going until you get it right. What is the name of our very first ever Mars rover? It was a little bitty dude. This is a long time ago. This is before your all's time. Nobody in this room, I think, knows it. Any guesses? Any guesses?
Sojourner?
Sojourner! I pronounce it Sojourner, but I mean, I could be wrong. I'm going to give you 3 of these NASA Meatball temporary tattoos. Share them with your friends, or not. I mean, you can put them all 3 on yourself if you really are that big of a NASA fan. Well, clearly I'm How about a big round of applause to all of our amazing volunteers. Now, it is time for the award ceremony. Who's excited for the award ceremony? And we're going to switch mics. Check, check, awesome. This mic works much better. I should have used it that whole time. All right. I'm looking for our first speaker. You guys have done amazing. It's Rich Johnnebeck. You guys have done an amazing job here this week. Firstly, you all competed last week. It was a very long, we're talking about 4 days, right? At UCF in Orlando. That was a lot. And then you did very well there and came here, and with only 1 day in between their competition and ours, you worked your tails off here for 3 long days. You're all away from home and under a lot of stress. So give all of yourselves a big round of applause for what you have been through over the last couple weeks. And now, please welcome to the stage Mr. Rich Johnnebeck, who wants to talk. Big round of applause, Rich Johnnebeck. I warmed him up for you.
Listen, thank you guys for coming out here. It is an absolute privilege to see you guys work, interact, the teamwork, cheering each other on, not as competitors, but as collaborators, colleagues. Brilliant, loved it. But first, I want to introduce Mr. Thad Altman. He's the president of the Astronauts Memorial Foundation. This is his facility, and we are here because of his generosity and the foundation's ability to support us. Mr. Altman.
Thank you, Rich, and what an inspiration has been to watch this competition. You know, we are a product of the tragic Space Shuttle Challenger accident. And our nation came together to support the construction of the Astronaut Memorial Mirror, which is designated by Congress as the Memorial for Fallen Astronauts. This center, the Center for Space Education, was a product of the revenue we raised. And this is here to promote the dream of those who've made the ultimate sacrifice. This event, you are a product of that sacrifice that our astronauts made to bring life into space. This event is a direct result of their dream and keeping their dream alive. We know as a society, if we're going to survive, ultimately, we have to be a spacefaring society. It's absolutely a necessity when you look at the time, the millions of years that we hopefully will exist. It's in your hands. You are a part of fulfilling that dream of making us interplanetary. And I can think of no other event that we host here that is more relevant to that. So your energy, your vision, your intelligence, your drive is really a part of keeping us as a species. I can't begin to emphasize the relevance and the significance of what you do. So thank you for being here. There's hope for the future, and you are the future. Thank you.
Thank you, Mr. Altman. So I just want to thank a few people here. This is not an endeavor of one, it's an endeavor by many. And because of all the people working, a lot of volunteers, we were able to bring this to you, and you were able to bring us new feats of technology, things that we haven't seen before, wheels, treads, feet, the program, and everything else. And the people that helped bring it out here is the Astronaut Memorial Foundation. I want to thank Caterpillar for their wonderful support through all these years, including Martha Bardoff, who has your team doing the vehicle inspection to make sure the robots were safe and within policy. Thanking UCF, who's another big part of our program. Thanking SwampWorks. Thanking all of the judges that were out here. Kurt, who's the voice of Lunabotics. Thanking LIDAR, Rigel, and all the folks that came out here. So once again, thank you very much. We've had a fantastic time. Kurt, lead us off.
Sorry, we just had a late addition. Give me just a sec. You understand how this goes. All righty. Thank you, Rich. Our next speaker, you all know, it is Eric Reiners from Caterpillar. Come on up, Eric.
Thank you, Kurt.
Nice.
Thank you, Kurt. So I'm going to be going over and introducing the RC, the Expert Lunar Operator Awards, and also the Caterpillar Autonomy Awards. But before I begin, I want to start by thanking our hosts for the last week and a half. University of Central Florida and the staff there, and the Astronaut Memorial Foundation, and all the hardworking staff here. I also want to thank NASA and their support of making this possible all these years since 2010. But most of all, I want to thank all of you and all of the hard work, effort that you've put in for the last 9+ months for this competition. I'm also very excited for all of you and all the things that you have been able to learn in the course of participating in this competition and how that's preparing you for industry and the workforce. And I'm very excited that some of you in just a couple of weeks are going to be joining that workforce at Caterpillar. So for those of you coming, go Team Caterpillar. And with that, I'm going to turn it over to Matt Fike, who's an engineering manager in our CAT Technology Group with Autonomy, and he's going to talk about Expert Lunar Operator Awards. Matt?
All right. Thank you, Eric. All right, it was exciting to see so many of you come up and operate the Caterpillar RC Command Station. So we want to do a little bit of stats here. We had 48 students and 8 staff participate this week. The average student time was 3 minutes and 21 seconds, which is a lot faster than our last competition and really good. And so I wanted to highlight, just like I did at UCF, the most students from one particular school. Does anyone have any guesses? With 14 students, it's the University of Virginia. Well, so someone clearly messed with my slide, but what I'm going to go through is one by one here, and I'll call off from fastest to slowest, and you'll come up to the stage and grab a prize of your choice. So starting with number 1, it is Craig Kalkworth, thank you, Craig Kalkworth, with 156 from the University of Virginia. Anything you want. All right. All right, it's less of a surprise. We have a pretty good sweep by the University of Virginia here. So, Ethan Edwards with 2 minutes. So those things are trash cans over here with the, yep, and the organizers. We got some toys over there. Trash cans for your car. All right, Cameron Spears in 3rd place with 204. Then in 4th place, Jameson Brocato with 208. All right, coming in 5th, somebody not from the University of Virginia. I know, shock. Eric Perez from the University of Miami. How are you here? All right, is Jamie not here? Or Eric, I mean? How about, if he's not here, I'm going to go to the next one, which is Zachary Parcia from the University of Virginia. Okay, and my fastest staff got cut off here a little bit, but is Jamie Peer from NASA here? All right. How about Dr. Scott Schaefer from San Diego State? All right. Thank you, Dr. Schaefer. All right, I think we're going to bring Eric back up, and he's going to announce another award. I'm not going to click. No. All right.
All right, so I'm going to do a unannounced, or I didn't put it on the slide at least, special recognition award based off what we said at UCF relative to a challenge on dozer rap. And a little recognition there, and that is to University of Virginia. Now wait, before you come up, just wait and be patient. And
Got the bass, stand on
University of Virginia, you can come up and take whatever's left, all the stuff that's left. This too. Sure. Perfect. Six. Okay. Perfect. Just grab it and distribute it. Just grab the whole thing and then pass it out amongst your team. Yeah. Thank you guys. It's the best wrap I've ever seen. So now I'm going to go into the Caterpillar Autonomy Awards. And I'm going to start off with just some stats and information. So between UCF and KSC, there were 27 teams that achieved autonomy points of some type. And so you can see across the categories of where teams were able to score. The count of the team was based upon of the 4 run opportunities, whichever one you scored the highest in. And so 27 teams is the most ever. An example, 2025, there were only 12. So this is tremendous. Yes. So that's over 50%, 57% of all the teams participating were able to do this. And so it's a huge achievement. Just a few years ago, weren't able to award all 6 places a few years ago. And so this is a tremendous success by the competition and all of you. So I'm going to start to get into the actual places. As I start to do that, though, I'm going to do an honorable mention for those teams that did score points but were not able to achieve places 1 through 6. So let's give a warm round of applause for all of them. And now I'll get into the actual placed points or in categories. You'll notice that Michigan Tech had 500 and there's a 6th place with a 500. The rule book indicates that tie is broken by the sum of the construction points from UCF and KSC. And so 6th place at $250 goes to College of DuPage. And I think College of DuPage, are you guys going to, okay. So we have some, I think, past alums of College of DuPage who are now on other Lunabotics teams, right? They're up here to accept on behalf of College of DuPage.
They're here in spirit.
Next at 5th place, again, $250 and 625 points, Iowa State University. Who's accepting this? Right here, right in front of the check. Well done. All right, thank you guys. Well done. Next, in fourth place, $500 and 670 points. Purdue University main campus. What's the weight limit on this stage? What? They just keep coming.
Yeah, step in front if you need to. Keep going.
All right. Thank you, Purdue. Well done. All right, so third place, $750 and 870 points is University of Utah. Let's go, Utes. Oh, you're hiding the, there you go, like that. All right. Go Utes. Second place for $1,250 and 1,100 points is University of Virginia. All right, University of Virginia. And first place for $2,000 with 1,400 points is University of Alabama. Roll Tide. All right. Thank you, guys. Well done. Thank you, and we'll turn it back over to Kurt.
Oh man, that was amazing. Thank you, Eric. Thank you, Caterpillar. An amazing job, teams. All right, right now, we have a special award. I would like to please help me welcome Beck Mazzone to the stage. Come on up, Beck.
guys. So for those of you who have been operating your robots here at Kennedy this week, you know that I've been the mission control director for the event this year. One of the things I love most about sitting in mission control is that it gives us a view of who you are as a team and how you function together, and the way you celebrate when things go right, and how much we learn about you when things don't quite go right. So as we looked across the teams and all of you come through and you bring something different, we felt that one of the teams that came through Mission Control this year really stood out to us. The reason this team stood out, one of them was attitude. We found this team to be extremely positive. They were enjoyable to have in the MCC. They were professional. They were calm and together, whether they were in expected scenarios or unexpected scenarios. They stood out to us for their teamwork. This was a team that to us presented genuine unity, right? They communicated effectively with one another. They were cohesive no matter what scenario they were in, what they were working on, and they seemed to enjoy being in it together. Some teams come through and they're a team, but I'm this person on this team and I'm this person on this team, and that cohesion isn't there. And so when we see it in teams like we did with this one, it really stands out to us. We also felt that this team was extremely resilient, that they were able to avoid losing their mission entirely. When they experienced an unexpected mechanical failure, they had experience with off-nominal modes of operating their robot, and this allowed them, without hesitation, to switch into a different way of looking at how to execute their mission. And they weren't just able to finish the cycle that they were on, but they were actually able to continue operating for the remainder of the time that they had and be successful, maybe not quite as much as they had started out as, but they were able to keep going and persist through it. And attributes like these are what we strive for in our teams at NASA. And they are the kinds of things that we look for in our young engineers, like all of you, who are going to carry our missions forward. And so on behalf of Mission Control, we would like to provide a Mission Control Center special recognition for mission excellence to UVA for exceptional team conduct, mission preparedness, and failure recovery. Welcome. We got the whole crew. I love this. You guys are great. Thank you guys.
Thank you. Awesome, congratulations. All right, next we're going to give out the Efficient Use of Communications Power Award. Please welcome Philip Michael to the stage.
The efficient use of time is to go on and incorporate the reality of the limitations that we have when we're communicating to things on the moon. It's the ratio between the regolith that you collected, the bandwidth that the robot uses, and also the other aspects such as the cameras that you use in the competition. This year, the Efficient Use of Com Award goes to Iowa State.
Philip, you can go. Thank you. Congratulations. I have a special award, and I hated to see you go all the way back and then have to be called back all the way up here again. I have a special award. Guess what award we are giving? Another award to the Iowa State team. We call it the Most Spectacular Failure Award. This is a brand new award this year, and here's your prize.
Oh, let's go.
Congratulations, Iowa State. Okay, sorry, pose, I'm new to this, sorry. Pose for a picture. Thank you. Congratulations, Iowa State. Oh, make sure you give the plaque back so that we can actually finish it. Thank you. All right. Next are the awards you've all been waiting for. We are about to give the Construction Awards. Come on up, Rob Mueller.
He's asking me, does this look right to you? I hope so. Okay, question number 1. Did you have a good time? Yeah! I know it's hard. I know it's hard, but it wouldn't be rewarding if it wasn't hard. They say the best things in life are when you overcome something hard. It's not worth it if it's not hard. So if it was hard, just pat yourself, everybody pat yourself on the shoulder right now. Okay, good job. Yesterday a journalist came to me and wanted to have an interview for an article that appeared in the Orlando Sentinel newspaper today. And I read it and said, oh, I wonder what he's saying about us. And he took a quote, which I didn't even realize I said because he was recording me while I was speaking freely. And I said something like, it's a symbiotic relationship. We learn and you learn from us and we learn from you. That's what symbiotic means. We depend on each other. So it's true. I personally have been watching the videos very closely. I believe we'd have a breakthrough in physics this week. No kidding, because the University of New Mexico did something which is not in the textbooks. They weren't driving anymore, they were swimming. Think about it, because a trick question I have when people come to the SwampWorks, I say, regolith is a granular material. Is that a solid, a liquid, or a gas? What's the answer? All three. The answer is yes. Whoever said yes, they're correct. All three. And today we saw regolith being churned up so much that it turned into a fluid. And a lot of you were driving in a fluid in 1G, but on the moon in 1.6G, it would be even more like a fluid. So now you have to start thinking, am I driving in a solid or a liquid? And just food for thought. I'm not going to answer that question. The other thing I want to say is, in our lab, we've got a new expression. Berm, baby, berm. And that's what the construction prize is all about. So, on the count of 3, berm, baby, berm. Ready? 1, 2, 3. Berm, baby, berm. Woo! All right. That's great. Now you know what the construction award is for. Berm, baby, berm. So, you're building a berm. And then I hate it when people say, this journalist said, it's a mound of dirt. It's not a mound of dirt. It's a highly engineered granular material, which is a civil engineering structure, and it will be the first off-Earth civil engineering structure built by humanity. That's what a berm is. It's a high-tech thing. So, and not only is it high-tech, you're doing it with a robot. That's even harder. And not only that, it's autonomous. Wow. Okay, without further ado, where are we at? Mission Control Director, we've done that. Lunabotics Construction Award. Hope this is right, Kurt. Third place for the Lunabotics Construction Award goes to Michigan Tech. Who's your team captain? Your team captain? Okay. I've been watching this team since 2010, and they should get the Heartbreak Award because they've almost won this competition 3 times that I can remember, only for something to break. So that is the Heartbreak team, but they're getting there. I think they'll win one day. With a great advisor, too. So second place goes to the University of Virginia. Good job, everybody. Now, the top prize for construction, remember, that's building the biggest berm. This is a shocker. First prize goes to College of DuPage. Unfortunately, they're on a flight home right now, so we'll have some alumni here. Good job. In case you don't know, College of DuPage is a community college. So take that. Just goes to show. All right, but it's not all about berms. The Off-World Grand Prize is really a combination of everything. You have to be good at systems engineering first. We really bring you here for robotics and excavation, but that's not really what you take away. You take away systems engineering skills, which you can apply to anything in life. Anything you do, backyard project, you can apply systems engineering to it. You're building a car, systems engineering, an airplane, systems engineering, building a skyscraper, systems engineering. It's just a fundamental way of working. So systems engineering is the skill, if you go for a job interview and somebody says, what do you have that nobody else has? You say, I'm NASA systems engineering trained. That's it. I've done NASA systems engineering. I've been through the whole process. That's something your competition probably doesn't have. So just remember that. So you've learned systems engineering, you've learned how to design, you probably had to do some CAD along the way and some calculations. So you've learned all that. But more importantly, after you've designed it, you've built it, hands-on. That's going to set you apart from most people around you as well. You've built it. And more than that, you felt the pain. You know, the pain of building something is hard, but you survived and you overcame it. So be proud of that. So that's why it's called the grand prize. It's more than that. You've done a presentation and a demonstration. You've learned how to do public speaking. You've learned teamwork. So when you wrap all that up, it's the grand prize. So this is a difficult prize to win, and it's not obvious because the team that built the biggest berm didn't win the grand prize. How can that be? We built the biggest berm. We should get the grand prize. No, because you used more energy. And other things that matter. You used more communications. You used more energy. Your robot was heavier. So when you go on a mission, it's not just one thing, it's everything in the system. So that's why the grand prize is not the biggest berm. It's the best system, okay? So you understand that. Now, I'm very happy to announce that the 2026 Lunabotics Artemis Grand Prize goes to the University of Virginia.
I don't know how. Broken real catastrophic. No, guys. Let's go. Let's go. Let's go. Let's go. Thank you, sir. Those are up.
Wow, that was crazy. All right, we have a special speaker, cheerleader that's going to come up and sign us off. Come on up here, Eric Reiners from Caterpillar.
So we kicked off the competition last week with a NASA Lunabotics shout out. And I can't think of any way better than to close out the week with a NASA Lunabotics shout out. So if you all stand up, I think you know the drill. I'm going to count down from 3, 3, 2, 1. And it's going to be NASA Lunabotics. Design it, build it, dig it. You guys ready? Yes. Are you ready? Yes. Here we go. 3, 2,
Great job, everybody. Thank you, everyone, for coming. I'm glad you all had a great time, and what amazing winners. Great job. That concludes our live broadcast. That concludes our event. Drive home safe, fly home safe, get your robots home safe. Goodbye from the 2026 Lunabotics event. Goodbye. We love you all. You're all winners in our book. You're all winners.